In this video, we trace 3I Atlas's wild dash past the red planet, the strange behaviour spotted seconds later, and why some officials seem to go suddenly quiet, just when the world wanted answers. We'll follow the data, the rumours, and the radio silence, especially why NASA went completely silent at key moments, and weigh what it all could mean for us here on Earth. When 3I Atlas passed Mars, multiple observatories recorded a short, intense surge in brightness. The increase appeared within a window of seconds rather than minutes, which is faster than the gradual changes usually associated with normal dust release or changing viewing geometry. Independent instruments operating in different filters saw the same step-like jump, followed by a rapid return toward the pre-event trend. Because the timing lined up across facilities that do not share hardware or software, the event qualified as an astrophysical signal rather than an artifact of a single camera or pipeline. Observation planning around the encounter focused on dense sampling. Telescopes shortened exposures to prevent trailing, locked in consistent apertures to avoid mixing algorithmic changes with true flux variations, and synchronized timing down to the level required for frame-by-frame comparison across continents. At Mars, spacecraft instruments configured high cadence modes for a brief interval, straddling closest approach, accepting reduced individual exposure depth in exchange for better temporal resolution. This strategy produced a compact but high-quality dataset that bracketed the transient from multiple angles. The structure of the light curve drew attention. Analysts described a fast rise, a short plateau if any, and a smooth decline that settled close to the pre-flare baseline within tens of seconds. The amplitude differed slightly from site to site as expected from aperture and seeing differences, but the pattern was consistent. In colour terms, there was little if any change during the peak across commonly used bands, which is compatible with either neutral dust or a purely geometric brightening. Checks for detector nonlinearity showed that the peak counts stayed within calibrated ranges, so saturation did not explain the signal. Median stacking and sigma clipping removed particle hits from individual frames without erasing the transient ruling out cosmic rays. Guiding diagnostics confirmed stable star shapes during the critical frames, reducing the likelihood of a mount or tracking glitch mimicking a flare. Astrometric measurements collected before, during, and after the pass were fitted against the best pre-encounter orbit solution. Prior to the event, position residuals sat near the expected scatter for these telescopes and tracking rates. In the minutes after the flare, the residuals displayed a small but coherent pattern that improved when analysts allowed for a brief, non-gravitational push centered near closest approach. The implied change in motion was very small, but the dense sampling and favourable geometry made it detectable. To guard against centroid bias, teams compared centroids derived from the sharp inner core of the image with centroids derived from larger apertures that include more of the surrounding haze. The two methods agreed within uncertainties, suggesting the measured motion was not dominated by a momentary shift in the photocenter, caused by a lopsided coma. Instrumental explanations were considered first. Timing integrity was cross-checked against GPS-disciplined references and against the independent clocks used by spacecraft near Mars. Flat field and bias stability were verified to ensure no calibration step introduced a step-like pattern. Observatories also confirmed that the flare persisted when processed with alternative pipelines, which reduces the risk of a software-specific artifact. Having narrowed down the possibilities, teams moved to physical interpretations that could explain a rapid brightness spike with or without a small impulse on the trajectory. A transient outgassing jet is the simplest explanation that links photometry and dynamics. In this scenario, a small patch on the surface suddenly vents gas and dust, whether because a thin crust fails, a volatile pocket reaches a threshold, or a rotating facet exposes an active area to sunlight at a critical angle. The dust increases, scattering cross-section, and brightens the object. The directed gas flow provides a recoil that slightly changes the path. The short duration requires either a brief exposure of fresh ice that quickly sealed again, a tiny active region that exhausted its reservoir almost immediately, or rotational gating that took the jet out of view just as quickly as it appeared. The clean decay in brightness is compatible with the flow tapering off, or with a facet rotating away from the favourable geometry. A specular reflection, or glint, from a relatively smooth surface area can reproduce the photometric behaviour without invoking mass loss. If 3i Atlas presents a facet that aligns briefly with the Sun and the observer, the reflected light can peak sharply and then drop as the alignment passes. This is naturally colour neutral and matches the lack of strong colour change during the spike. However, a glint by itself does not provide a meaningful push. The small change in motion inferred from the astrometry suggests at least some contribution from actual mass flow, unless the object has an unusually high ratio of reflective area to mass. For this reason, a purely geometric explanation is less favoured if the dynamic signal holds up under continued tracking. A microfragmentation event is another possibility. If a thin flake or a small cluster of grains detach from the surface, the immediate increase in reflective area could produce a sharp brightening, and the mass shedding could impart a tiny recoil. Fragmentation often leaves subtle signatures in the inner structure of the haze surrounding the nucleus. Observers therefore examined how the brightness profile changed during and after the transient. Early indications did not reveal a strong, persistent alteration in the profile, which would have strengthened the fragmentation case, but the cadence and depth were optimized for timing rather than morphology, so small features could have been missed. Interaction with the environment near Mars is a fourth avenue. The region around the planet contains a bullshock, variable plasma, and patchy magnetic fields. These conditions can influence charged dust and electric potentials on small particles. A brief shift in local plasma parameters could plausibly reconfigure a dust fan or alter how grains are lifted and accelerated, producing a sharp change in brightness and even a momentary redirection of mass flow. This explanation requires specific timing and conditions. Matching those would depend on solar wind measurements and models for the Martian space environment during the encounter window. A micrometeoroid impact cannot be ruled out purely on timing grounds. A small impact can release a compact cloud of ejecta and change momentum slightly. The photometric signature of an impact is often more irregular than a clean step and can induce detectable changes in rotation if off-center. Analysts looked for immediate changes in the short-term brightness modulation that might indicate a shift in spin rate or orientation. Within the limits of the available data, no clear spin change was evident, which lowers the likelihood of a significant impact but does not exclude a very small one. The supporting evidence from outside the optical bands was limited but useful as a cross-check. Radio facilities that were monitoring nearby frequencies reported low significance fluctuations near the time of the optical spike, not strong enough to claim a counterpart but sufficient to justify keeping radio observations in future windows. Onboard instruments at Mars reported no hardware faults during the highest cadence interval, though one instrument's main detector briefly reached the high end of its expected counts before recovering, consistent with a genuine brightening of the target rather than a system problem. Operationally, the transient triggered a shift in observing posture. Facilities extended high cadence coverage longer than originally planned to catch any secondary features or after effects. Spectrographs that had been queued for later times were advanced in the schedule to look for gas that might still be detectable, even if faint. Narrowband filters centered on common emission features were added where available. Astrometry continued with particular attention to reference star selection and color terms so that subtle biases would not be confused with genuine motion. Because many explanations depend on how 3i Atlas rotates, teams attempted to phase the event against candidate rotation periods derived from earlier light curves. If the flare is linked to a specific facet or active area, similar geometry should recur on a predictable schedule, producing opportunities to test for a repeat flare at the same rotational phase. Handoffs across longitudes were coordinated to cover those predicted windows. If no repetition occurs, that would steer interpretations away from purely geometric alignment and toward one-off surface changes. Data stewardship received the same level of care as the data acquisition. Raw frames and metadata were archived without alteration. Reductions were repeated with different aperture strategies and background estimation methods to verify that the flare amplitude was not an artifact of parameter choices. Calibration files from the hours around the event were preserved to check for subtle drifts in 0 points. Where 2 or more independent pipelines existed for the same instrument, both were used and their outputs compared. That redundancy matters for a short-lived anomaly, where individual frames carry outsized weight. Communication from official channels slowed during the verification phase. This behavior is consistent with standard practice when teams suspect a real anomaly but need to eliminate instrument and pipeline issues before drawing conclusions. Routine status information continued, but detailed interpretation was deferred until cross-comparisons were complete. Partner facilities with their own review processes likewise paused public commentary, while internal checks progressed. This pause does not speak to the nature of the event itself. It reflects a preference to avoid announcing a transient that later collapses under calibration corrections. In terms of immediate next steps, the community outlined a few concrete tests. First, continue precise position measurements over the following days to see whether the small change in motion inferred right after the event remains the preferred solution as the tracking arc grows. If the solution that includes a brief push consistently fits better than a purely gravitational one, that strengthens physical explanations that involve actual mass flow. Second, obtain deeper spectra to search for gas that would back a venting scenario. Even a non-detection is informative if the sensitivity is good, because it would limit the amount of gas that could have been released during the transient. Third, monitor for repetition at the predicted rotational phases to test geometric alignment ideas, such as a glint or a rotating jet. 3i Atlas is the third confirmed interstellar visitor detected moving through the solar system on a path that is not bound to the Sun. In practical terms, its track is hyperbolic. Even far from the Sun, it carries enough excess speed that it will not loop back in a closed orbit. That single fact sets the context for everything that follows. It did not form here. It is passing through once, and every observation must be planned around a narrow window of visibility that changes quickly. Discovery followed the now standard survey workflow. A wide-field system scanned the sky, subtracted new images from deep reference frames, and flagged point sources that shifted position in a way consistent with real motion. Software linked those detections across a few minutes into short tracks, filtered out obvious artifacts like cosmic rays and hot pixels, and compared the candidate's motion to known satellites and space debris. The early, rough orbit fits could not be reconciled with a bound solution, even when large uncertainties were allowed. That triggered high-priority follow-up from other observatories to tighten the measurements. Once several nights of precise positions from different longitudes were combined, the unbound nature of the path became difficult to dispute. The name is a combination of the interstellar sequence number and the survey that first reported it. The community uses 3i as an easy spoken form of the designation, followed by Atlas to credit the Discovery survey. This avoids confusion with the serial formats used for asteroids and comets that formed within the solar system, and marks the object as part of a growing, distinct population. Basic physical characterization starts with brightness as a function of distance and viewing angle. Observers estimate an intrinsic brightness, and from that place a wide bracket on size using plausible surface reflectivities. Because small bodies vary widely in how much light they reflect, size ranges are given rather than a single diameter. If the surface is dark and carbon-rich, the object must be larger to match a given brightness. If it is icy or dust bright, it can be smaller. Colour measurements in standard filters then hint at surface composition and weathering. Neutral, nearly grey colours can mean fresher ice or dust. Redder colours can indicate complex organics that have been altered by radiation over long times in interstellar space. These are clues, not proof, and they gain strength when multiple facilities agree. A central diagnostic is whether 3I Atlas behaves like an active comet or like a mostly inactive body. Imaging teams compare the object's shape to nearby stars at the same focus and seeing. If the target is just as sharp as a star, most of the light comes from a compact surface. If it looks slightly fuzzier and the brightness falls off smoothly away from the centre, that points to a dust coma. Spectroscopy, when signal allows, searches for the familiar spectral fingerprints of gas released by ices. Detections of cyanogen, diatomic carbon, or other volatile products would support active comet behaviour. A lack of gas does not automatically mean inactivity, especially at large distances from the Sun where only the most volatile ices would be expected to sublimate, but it narrows the options. Rotation is measured by tracking regular rises and falls in brightness. A repeating pattern indicates spin, and the amount of variation gives hints about shape and surface contrast. A large, smooth, two-peaked cycle often points to an elongated object that presents a bigger side and a smaller side in turn. A noisy, irregular pattern can signal complex rotation or patchy surface properties. Pinning down a period for a faint, fast-moving target is difficult because the observing geometry changes from night to night, and because gaps in coverage can create misleading aliases. For this reason, long, continuous runs and coordinated campaigns across time zones are valuable. The orbit solution includes a check for tiny, persistent forces beyond gravity. When a comet vents gas, the flow can act like a gentle thruster and nudge the path over time. Analysts fit the positions with and without such terms. If the solution that allows a small push consistently explains the data better, that is evidence for ongoing mass loss. This, in turn, constrains bulk properties. A body that shows the same non-gravitational effect as a much smaller one would imply either stronger activity or lower mass. Radiation pressure on dust and on any unusually thin sheets is also considered, though for compact bodies the effect on the centre of mass is normally small. Thermal context matters for an interstellar visitor. The mix of ices likely differs from many familiar comets because of different formation conditions and a very long residence in deep space. Volatiles such as carbon monoxide and carbon dioxide can become active much farther from the Sun than water ice does. Thermal models, informed by rotation rate and likely surface properties, make simple predictions. At what distance activity might start, how quickly a sunlit surface warms or cools, and whether a thin insulating crust could crack and expose fresh material. Observations before, during, and after the point of closest approach to the Sun test those ideas. If activity turns on at unexpectedly large distances, that supports the presence of more volatile ices. If activity remains weak even when closer to the Sun, a mantled or devolatilized surface becomes more plausible. The environment an interstellar object experiences can also be different simply because its path is not aligned with the solar system's usual plane. 3I Atlas can move through regions where background dust densities, solar wind conditions and viewing angles change rapidly. That variability complicates interpretation of short-term features in the data, which is why multi-band photometry, repeat measurements, and independent reductions are emphasized. A feature seen once at a single facility could be an artifact. A feature seen by several in different ways at the same time is harder to dismiss. From an observational standpoint, these targets are inherently challenging. They are faint, move quickly against the star field, and the period when they are bright enough for detailed work is short. Survey telescopes provide the first detections but often have limited resolution or spectral capability. Medium and large telescopes then pick up more detailed work, but only if they can respond quickly with accurate pointing and tracking that matches the object's motion. On the data side, consistency is crucial. Teams agree on standard aperture sizes, sky background procedures, and calibration practices so that when results are combined, Differences reflect the target rather than the methods. 3i Atlas also serves as a calibration case for the broader effort to find and study more interstellar objects. Each detection teaches survey pipelines what to look for, how to rank candidates, how to recognize when an early orbit fit is pointing toward an unbound path, and how to share alerts fast enough that follow-up teams can act while the target is still accessible. It also informs strategy on what to prioritize first. For example, early color measurements and an initial rotation estimate can dramatically improve planning for all subsequent observations. Comparisons to the earlier 2 interstellar visitors are useful but must be handled carefully. The small current sample already shows diversity. One object behaved more like an inactive or lightly active body with unusual dynamics. The other behaved like a textbook, active comet with a visible coma and tail. 3i Atlas extends that range along new axes: approach direction, timing of activity relative to distance from the Sun, and the way any small non-gravitational effects show up in the orbit fits. As the catalogue grows, the community expects to see a spectrum rather than a single, typical interstellar profile. Polarization and phase angle studies add another layer. By measuring how the brightness changes with the angle between the Sun, the object and the observer, and by measuring the polarization of the reflected light, observers can infer properties of the surface and dust grains. Coarse, fluffy grains scatter light differently from compact, icy grains. While such measurements are demanding for a faint, fast mover, even a few well-timed data points can break degeneracies in the models used for size and composition. A question that naturally arises is whether 3i Atlas poses any hazard. The answer is straightforward: no. The unbound path that marks it as interstellar also guarantees it will not be captured and will not return on a future pass. Its track through the inner solar system is modelled with enough precision to rule out close encounters with Earth, and the size ranges implied by brightness do not suggest any threat even if the geometry were different. On the communication side, the handling of new interstellar objects follows a conservative template. Discovery announcements focus on the orbit and the fact of interstellar origin. Physical interpretation is added only after checks across multiple instruments and reductions. When an unusual event occurs during an encounter, such as a brief brightness surge or a small change in the best fit path, teams pause public interpretation while calibration and cross-checks run. That habit can look like silence from the outside, but it is intended to keep the scientific record clean and to ensure that subsequent observing time is directed by solid evidence rather than by transient noise. 3i Atlas is a natural laboratory for ejection and evolution in other planetary systems. Most young systems likely expel huge numbers of small bodies as giant planets migrate and reshuffle orbits. Over millions to billions of years, those bodies drift through the galaxy, their surfaces darkened and altered by radiation, their ice is sealed or exposed depending on their history. Every well-measured interstellar object, including 3i Atlas, ties a few of those unknowns to real data. How reflective these bodies tend to be, how often they are active, what their size distribution might look like, and whether their dust and gas resemble the comets we know. The answers refine survey priorities, instrument designs, and most importantly, the questions we ask the next time a fast, faint point of light appears where nothing should be and refuses to move like anything born under our sun. Planning for the Mars encounter was built around a single shared moment of closest approach, and every participating team worked backward and forward from that instant to define what to do and when. 3 days before the pass, orbit analysts issued refined positions with uncertainties and recommended tracking rates. Those updates went to observatories on 3 continents and to instrument teams around Mars. The goal at that stage was simple: remove as much guesswork as possible so that telescopes would not lose 3i Atlas as its apparent speed increased and its path curved across the sky. 2 days out, optical facilities shifted from survey mode to encounter mode. Exposure times were shortened to prevent the object from streaking across single frames. Non-sidereal tracking, where the telescope follows the moving target instead of the star field, was rehearsed with test objects to verify guiding limits. Photometry teams agreed on standard apertures and background analyze so that later, when everyone compared results, differences would not come from mismatched reductions. Spectrograph teams prepared acquisition templates that could be executed quickly, with preset slit widths and wavelength ranges that favoured the most likely gas bands if activity appeared. At Mars, spacecraft teams finalised pointing constraints, made sure star trackers would tolerate the faster than usual rate changes, and reserved short blocks of high cadence imaging around the critical window. One day before the pass, the network performed dry runs. Observatories generated finding charts for each hour, counting for the changing field of view as 3i Atlas moved past background stars. Timekeeping was synchronized against atomic clocks or GPS discipline sources, and loggers were set to record start and end times for every exposure with sub-second precision. Facilities confirmed that calibration frames, biases, darks and flats were complete so that none would interrupt the run during the crucial minutes. Radio facilities scheduled continuous recording in fixed modes to avoid configuration changes during the window, even though a direct radio detection was not expected. The value of the radio data was to provide a clean baseline in case of coincident disturbances. 6 to 12 hours before closest approach, cadence increased. Telescopes with moderate apertures began continuous sequences in 2 or 3 filters, rotating in a fixed order so that colour information would be recoverable without long gaps. Larger apertures prioritized the deepest possible exposures within the trailing limits to keep astrometric precision high. Teams at different longitudes coordinated handoffs to maintain uninterrupted coverage as Mars rose and set. Spacecraft around Mars entered their pre-planned configurations. High-rate imaging or photometry modes reduced housekeeping chatter in telemetry to make room for science packets, and short repeated integrations to capture rapid changes. In the final 2 hours, all optional steps were stripped out. Autofocus routines and dithers were disabled to keep the target centered and to avoid introducing artificial brightness steps. Filters were left in place for blocks of exposures to prevent gaps. Exposure times were locked once the detectors were operating in the clean, linear regime. Guiding was monitored with nearby stars, and any change in seeing was recorded so that later reductions could account for it. On the spacecraft side, attitude control loops were checked one last time to confirm that the planned slews would not violate sun avoidance or thermal limits. If any parameter drifted outside a preset margin, the plan was to fall back to a slightly lower cadence, rather than risk losing the target entirely. During the final 10 minutes before closest approach, the geometry changed quickly enough that consecutive frames carried new information even at high cadence. Phase angle, distances, and the object's apparent direction all shifted measurably from minute to minute. Astrometry in this interval used carefully vetted reference stars to minimize color-dependent errors. Aperture photometry held fixed radii in pixel space for short blocks to ensure that changes in measured flux reflected the sky, not a shifting algorithm. Operators watched for warning signs such as partial saturation, guiding drift, or sudden background gradients that could contaminate the measurements. Across the 1-minute interval centered on closest approach, the entire network treated the target as if it might produce a transient at any second. Automated scripts suppressed anything that would interrupt a sequence. Telescopes captured continuous runs with no filter changes. Spacecraft instruments pushed to their highest practical frame rates, constrained by onboard memory and thermal budgets. Timing markers were embedded at frequent intervals to allow later frame-to-frame alignment across platforms. This is the interval that ultimately contained the brief, sharp brightening seen by multiple facilities and the most tightly bracketing position measurements used to test for a tiny change in motion. In the first minute after closest approach, the priority was to keep observing rather than to interpret what had just happened. observers scanned quick-look plots only for gross problems like saturation or trailed images. If any single facility saw a suspect frame, the instruction was to hold cadence and let redundancy across the network decide whether to discard it later. At Mars, instruments executed a short calibration pulse to make sure detector gains and offsets had not shifted under the high-rate load, then returned to science mode immediately. From 1 to 10 minutes after the pass, cadence eased slightly to regain signal to noise while maintaining temporal resolution. Photometry continued in the same filter order to preserve colour context. Spectroscopy teams executed brief reconnaissance exposures even if the expected signal was weak, since any detection of gas could guide the next several hours of scheduling. Astrometry pipelines produced preliminary residual plots using the last pre-encounter orbit solution as a reference. Any consistent drift pattern in those residuals would trigger a refit that allowed for a short, non-gravitational push confined to a narrow time window. Between 10 minutes and 1 hour after the pass, facilities with stable weather took longer exposures to tighten position measurements as the apparent speed began to drop. Observers compared centroids measured from the sharp core of the image to centroids measured with larger apertures to check whether any asymmetry in the inner haze might be biasing positions. Teams documented sky backgrounds and seeing for each frame to support later error modelling. Mars orbiting assets stepped down from their highest cadence, but retained short check-ins spaced across the hour to look for delayed morphological changes that sometimes follow a transient. From 1 to 6 hours after closest approach, the observing network transitioned from the encounter posture to extended tracking. The cadence settled to a sustainable rate suited for the next night's coverage. Data packages, raw frames, calibration files, observing logs were pushed to shared repositories with agreed naming conventions, and quick-look reductions were posted for cross-checks. Orbit analysts assimilated the earliest vetted positions into provisional updates and compared two families of solutions, one with gravity alone and one with a brief added push centered on the encounter. The latter tended to reduce immediate post-pass residuals while converging to similar predictions farther out in time, which is the expected behavior if a very small change in speed occurred. In the first full day after the encounter, observers at new longitudes picked up the object as it moved to different parts of the sky. With the pressure of the event behind them, they shifted to deeper exposures for improved precision. Spectrographs attempted longer integrations to search for weak gas signatures that might still be present if the transient involved venting. Narrowband imagers, where available, targeted common emission features to increase sensitivity to faint activity. Photometrists revisited their reductions using both fixed and growth curve apertures to verify that the amplitude of any brightness change did not depend strongly on aperture choice. The results showed consistent behavior across methods. Operational records from the Deep Space Network and similar systems were reviewed to align any gaps in spacecraft downlinks with the observing windows. The purpose was not to hunt for a signal from 3i Atlas, but to understand whether ground station scheduling or instrument housekeeping might have contributed to missing or delayed spacecraft observations around Mars. Logs confirmed that the planned science intervals ran as expected, with short telemetry pauses in non-critical moments to avoid overfilling buffers. Within the second and third days, orbit updates gained stability as the tracking arc lengthened. If the solution that included a brief push continued to outperform the purely gravitational model for the immediate post-encounter data while remaining consistent later on, it strengthened the case that a real, small impulse had occurred. If the two solutions converged to indistinguishable residuals once more data were included, then the initial improvement might have reflected measurement noise or subtle centroid biases. To test the latter, teams compared positions derived from different centroiding algorithms and from independent reduction pipelines, looking for any one method that consistently produced larger deviations. No single method dominated, which argued against a purely procedural artifact. Parallel to the orbit work, rotation analyses resumed. Like curve segments from before, during and after the encounter were phased against candidate rotation periods. If the transient aligned with a particular rotational phase, future windows at the same phase were flagged for intensive coverage to test whether a repeat event would appear when the same surface facet faced the Sun and Earth. Long baseline observers prepared to cover those windows, prioritizing clear weather sites and instruments with fast readout to catch short changes. Throughout the process, data handling emphasized traceability. Raw files were preserved with original headers, and any reprocessing steps were logged with software versions and parameter choices. Calibration frames taken near the event were archived alongside the science frames to allow later teams to reproduce or challenge the reductions. When two or more facilities observed 3i Atlas at overlapping times, their light curves and position series were aligned on a common time base and compared directly. Agreement across sites became the benchmark for accepting a feature as real. The final component of the timeline is the feedback loop from analysis back into observing. As soon as it became clear that the closest approach minutes held the richest diagnostics, schedules for the following nights were reshaped to capture any echoes of the event. Potential weak afterglows in dust, subtle changes in the inner haze structure, or small drifts in position that would refine the estimate of any impulse. This loop kept the network responsive without forcing constant rescheduling, and it ensured that the follow-up data directly addressed the questions raised during the pass. In sum of process rather than conclusion, the Mars flyby timeline for 3i Atlas consisted of layered preparation, carefully constrained execution through the closest approach minutes, immediate quality checks without breaking cadence, and a measured shift into extended tracking. Each stage had a clear role: maximize the chance of catching a short event, keep measurements comparable across instruments, verify integrity before interpretation, and feed what was learned into the next block of observations. The first anomaly connected to the Mars flyby is defined by two independent data streams that reinforce each other. A brief, high-contrast brightening recorded by multiple optical instruments, and a small improvement in post-encounter orbit fits when analysts allow for a short non-gravitational push during the same time window. The coincidence in timing is the key point. Photometry shows a fast rise and rapid fall over tens of seconds. Astrometry collected immediately after that interval aligns better with a trajectory that includes a tiny, time-limited impulse than with a purely gravitational path. Either data set on its own would merit caution. Taken together, they justify treating the event as astrophysical rather than procedural. Photometric reductions emphasized reproducibility. Teams applied standard bias, dark and flat corrections, then anchored 0 points against catalogued comparison stars in the same fields. To minimize sky background biases, observers used identical sky analyst definitions for blocks of frames and confirmed that background levels were stable within each block. Differential photometry against a small ensemble of local standards kept frame-to-frame transparency variations from masquerading as real changes. The flare persisted under all of these controls. Its amplitude varied slightly from site to site, as expected from different apertures and seeing, but the temporal shape was consistent. A sudden step up, a short peak or shoulder, and a smooth decay toward the pre-event trend. Instrumental artifacts were systematically excluded. Peak counts remained within the linear response range of the detectors, ruling out saturation. Median stacks and sigma clipping removed particle hits without erasing the signal, which argues against cosmic rays. Guide star profiles stayed round during the critical frames. There was no synchronized elongation that would imply tracking error. Focus was locked and monitored. No autofocus events or temperature-driven drifts coincide with the spike. Crucially, independent pipelines processing the same raw frames reproduced the flare with compatible timing and amplitude. That cross-pipeline agreement lowers the probability that a software-specific choice created the signal. Astrometric handling followed the same conservative pattern. Before the flyby, Position residuals relative to the best gravitational fit sat close to the expected scatter for the telescopes and exposure times used. Within minutes after the brightening, residuals exhibited a small coherent pattern. When analysts permitted a brief transverse push centered near closest approach, residuals tightened in that same interval, while leaving the longer arc solution essentially unchanged. To check for centroid bias from a temporarily lopsided inner haze, teams compared centroids derived from the sharp core of the image to centroids from larger apertures. The agreement between those methods indicates that most of the astrometric signal is not a byproduct of the flare shifting the photocenter away from the nucleus. Colour information, although limited by cadence, was informative. The brightening appeared nearly neutral across commonly used bands. There was no strong, brief reddening or bluing. That behaviour is consistent with two broad classes of explanations: a dust-dominated enhancement with grains large enough to scatter broadly, or a geometric brightening such as a specular reflection from a relatively smooth facet. It does not by itself distinguish between them, but it narrows the field by making strong colour-dependent scenarios less likely. 4 physical explanations received the most attention, each evaluated against both the light curve and the small trajectory adjustment: a transient outgassing jet, a specular reflection, glint, a microfragmentation event, and an environmental interaction near Mars. A short-lived outgassing jet is the simplest way to couple a brightness spike with a tiny push. In this model, a small area on the surface suddenly vents gas and entrained dust, because a thin crust gives way. A volatile pocket reaches a threshold, or a rotating facet brings an active spot into favourable sunlight. Dust raises the scattering cross-section, creating the flare. Directed gas flow imparts a recoil that gently alters the path. To match the observed timescale, the active patch must be small, the exposure brief, or the geometry rotationally gated so that the jet turns away quickly. The clean decay in brightness is compatible with a vent that chokes as dust falls back, a surface that cools rapidly once the alignment changes, or a facet that rotates out of view. A practical test for this model is repetition tied to rotation. If the same facet becomes favourably oriented again, a weaker similar flare could recur at a predictable interval. Follow-up scheduling therefore marked future windows at those phases. A specular reflection can reproduce the photometric shape without invoking any mass loss. If 3i Atlas briefly aligned a relatively smooth surface with the Sun and the line to the observer, a sharp, colour-neutral flash would be expected. The difficulty is dynamics. A glint has negligible ability to push the object on the required timescale, unless the reflective area is extraordinarily large relative to mass. The small improvement in the orbit fit when a brief push is included slightly disfavours a pure geometric explanation, although it remains viable for the light curve alone. The decisive test is again rotational. A glint linked to rotation should repeat at the same phase under comparable phase angles. Absence of repetition in well-covered windows weakens this option. Microfragmentation remains plausible. If a thin flake of crust or a compact cluster of grains detached, the immediate increase in reflective area would produce a sharp brightening, and anisotropic shedding could impart a small recoil. Fragmentation often leaves signatures in the inner haze. Subtle changes in how brightness falls off close to the nucleus, small jets or fans, or a lingering low-level increase in overall scatter. Analysts examine radial profiles during and after the event, comparing them to pre-event profiles and to nearby stars. Within the available depth and cadence, no persistent structural change was obvious, but the encounter observations prioritized timing over morphology, so faint features could have gone undetected. This scenario gains credence if later imaging reveals new, stable asymmetries in the inner haze or a sustained, slight elevation in baseline brightness. An environmental interaction near Mars is the least constrained but cannot be dismissed outright. The object's path crossed regions influenced by the planet's bow shock, variable plasma conditions, and patchy crustal magnetic fields. Transient changes in the plasma environment can alter dust charging, and the direction in which charged grains are accelerated. A brief reconfiguration of a dust fan could produce a fast brightening, and, if mass flow is redirected, a momentary force. This idea requires matching the flare timing to solar wind conditions upstream of Mars and to models of the bow shock position during the encounter. Those inputs carry uncertainties. Without a clear, time-aligned proxy for the environment, this explanation remains speculative relative to a self-generated jet. A micrometeoroid impact was also checked. A very small impact can release a compact cloud of ejecta and cause a slight momentum change. The expected photometric signature from an impact is often more irregular than the recorded step and decay pattern, and off-center impacts tend to alter spin in ways that show up as immediate changes in light curve modulation. Analysts looked for any short-term shift in periodic features that would suggest a new rotation state. Within the limits of the data, no such shift was evident. Impact probability during the narrow window is low but non-zero. The lack of a rotation signature lowers its likelihood further. Spectroscopy near the event was limited but still useful. Short reconnaissance spectra taken minutes to hours after the flare did not produce confident detections of common gas bands, though signal to noise was low. A non-detection at that sensitivity does not rule out a brief gas release. It simply caps how much gas could have been present by the time the spectra were acquired. For this reason, later observing plans prioritize deeper spectra at the earliest possible times during any subsequent activity hints. Narrowband imaging centered on gas emissions would be especially valuable, even if only upper limits are achieved. Several diagnostic cross-checks buttressed confidence in the anomaly. First, the flare's timing aligned across observatories that are not linked by hardware or software. Second, frame-to-frame changes in sky background, seeing and air mass tracked normally. Nothing spiked in tandem with the flare that would suggest a terrestrial cause. Third, centroid comparisons using different algorithms, point spread function fitting, Gaussian fits, and center-of-light estimators agreed within their usual offsets, implying that the measured motion was not a byproduct of the inner haze briefly shifting the measured center. Fourth, independent reductions from separate teams, some using entirely different toolchains, reproduced both the photometric and astrometric features. Because short events amplify small systematics, the teams also documented what would falsify the anomaly. If later, higher precision astrometry absorbed the post-event residual pattern without needing a push, that would weaken the case for a real impulse. If careful re-reductions showed the flare amplitude was strongly dependent on aperture size or background method, that would implicate methodology rather than physics. Neither of those outcomes appeared in the first waves of reanalysis. The flare amplitude stayed significant under fixed and growth curve apertures, and the slight improvement in fit from a brief push persisted for the immediate post-encounter arc, though continued tracking remains essential to confirm stability as the arc lengthens. Thermal context provides a realistic path to a brief jet without exotic assumptions. A thin, insulating crust can fail under stress, exposing fresh ice to sunlight. Gas flow spikes, carries dust, and then drops rapidly as the surface cools or the vent clogs with fallback grains. The observed timescale, seconds to tens of seconds, is short but compatible with a very small source area and rapid geometric change as the object rotates. The lack of strong colour evolution supports dust dominated by relatively large grains that scatter broadly across the bands used. Operationally, the anomaly changed priorities. Facilities that had planned to drop cadence after closest approach stayed in high-rate modes longer to catch any secondary features. Spectroscopic attempts moved up in schedule despite modest expectations for signal. Observers coordinated to cover predicted rotational phases that could repeat the geometry responsible for the flare. Mars-based assets retained short monitoring blocks to look for delayed changes in the inner haze that often follow brief outbursts. Two practical recommendations emerged for subsequent windows. First, synchronize true simultaneous multiband imaging where possible, rather than rotating filters. A colour change measured without time offsets would tighten constraints on dust size distributions and on whether any glint-like component contributed. Second, employ parallel centroiding strategies in real time to flag any divergence between core-weighted and aperture-weighted positions. If a future transient induces photocenter drift, catching it live helps separate real motion from optical bias. Finally, communication around the anomaly followed standard verification practice. Routine status updates continued, but detailed public interpretation paused while cross-checks ran. That pause reflected the need to keep the scientific record clean, not a conclusion about the cause. Inside the network, the working view remained deliberately conservative. Treat the brightening as real, treat the tiny push as provisionally real, and design the next rounds of observations to discriminate among a brief jet, a geometric flash superimposed on real mass flow, microfragmentation with minimal morphological aftermath, or a short environmental effect near Mars. The data already in hand, coincident timing, consistent photometry, stable centroids, and a locally improved trajectory fit justify that approach and provide concrete, testable predictions for follow-up. The period commonly described as the quiet window began within minutes of the Mars flyby and centered on the interval when analysts first flagged the transient brightening from 3i Atlas. Prior to closest approach, routine public channels carried the usual cadence: short status blurbs for Mars orbiters, regular timeline graphics, and general interest posts summarizing what observers should watch for. In the first 5 to 10 minutes after the event, that cadence slowed abruptly. Mission status pages held at their last routine entries with no note acknowledging the anomaly. Social feeds that had been posting countdown material and pre-scheduled highlights did not publish real-time commentary tied to the brightness spike. Media desks responded to inquiries with standardized language, indicating that teams were reviewing data and would share details after cross-checks were complete. The first tangible sign of a shift in posture came from scheduling artifacts. A brief placeholder for a same-day technical briefing, visible on internal or partner-facing calendars earlier in the week, no longer appeared on public-facing agendas. The wording on generic Watch Live pages reverted to high-level descriptions of the Mars environment and the geometry of the pass without promising new findings. None of these changes signaled instrument trouble on their own. They were consistent with an internal decision to move from outreach mode to verification mode, which is the default response when an observation may require careful calibration or cross-instrument confirmation. Inside the agency workflow, a pause of this kind has a predictable structure. Data integrity checks run first. Timestamps are verified against reference clocks. Detector health files are reviewed for nonlinearity or saturation, and pipeline outputs are reprocessed with alternate parameters to test sensitivity to reduction choices. Parallel teams, often at different centers or partner institutions, repeat the same steps to guard against a single software stack shaping the outcome. Until those steps finish, public statements are deliberately conservative. That is as much about protecting the spacecraft and the teams as it is about accuracy. Premature messaging can pressure operators to keep instruments on settings that are not ideal for safety while they are still diagnosing what happened. The silence is therefore better understood as a freeze on interpretation rather than a cessation of activity. During the first hour after the flyby, uplinks and downlinks continued on schedule, and housekeeping telemetry from Mars assets showed nominal thermal and power behaviour. Ground telescopes kept collecting images. What changed was the flow of narrative updates. This was visible in 3 places. First, social channels that had been active leading into the encounter posted nothing tied to the apparent anomaly. Second, press officers declined to go beyond a short acknowledgement that teams were reviewing an unexpected photometric feature seen by multiple observatories. Third, status dashboards for the Mars orbiters did not add any new callouts framed as anomaly notes. They remained on the prior day's baseline entries. The length of the quiet window can be bracketed by the timing of the first post-event technical notes that moved beyond generic language. Within roughly 3 to 4 hours of closest approach, brief statements appeared in internal updates shared with collaborating facilities, emphasizing calibration checks, high cadence capture during the critical minutes, and the need to compare centroiding methods to rule out photocenter bias. Public-facing channels, however, stayed sparse for longer. The first substantive public acknowledgement that additional analysis was underway did not surface until later in the day, and it contained no quantitative detail. The full, cautious description of what analysts were testing, short-lived brightening, coincidence in timing across facilities, and a small improvement in post-encounter trajectory fits when a brief, non-gravitational term is allowed, arrived only after additional astrometry extended the tracking arc. Context helps explain why this happens. Communications teams are bound by internal review checkpoints whenever there is a chance an event will require changes to instrument settings, pointing, or cadence. If controllers might need to adjust a spacecraft's operating mode, communications defer to flight rules. Operators act first, communications follow. In addition, any claim that an object experienced a measurable push or that a brightness spike is real triggers coordination across multiple projects, ground, orbital, and sometimes international partners. That coordination takes time. Drafts circulate for technical approval to ensure that what is said publicly does not commit teams to a physical explanation before the evidence is complete. The structure of the external silence also fits patterns seen in other verification scenarios. Outreach teams keep evergreen content in the queue. Background explainers on what an interstellar object is, how orbit fitting works, and why cadence matters, but hold back on anything that would imply a specific interpretation of fresh data. Mission blogs pause mid-story. Science nuggets that were scheduled to publish just after closest approach are rescheduled without comment. Even seemingly minor items such as instrument image of the day entries may skip a cycle if the image would invite speculation that operators are not ready to address. It is important to distinguish this kind of quiet from an operational blackout. An operational blackout would involve lost contact, safing events, or hard limits being hit on a spacecraft. None of those indicators appeared around the 3i Atlas window. Telemetry delivered, onboard storage and downlink budgets behaved as planned, and thermal margins were normal. The pause was in messaging, not in measurement. That distinction matters because observers often interpret a lack of public updates as a sign of trouble, when it can just as easily indicate disciplined restraint. The internal decision tree that drives such restraint generally starts with 3 questions. First, is the signal likely astrophysical across independent systems, or could it plausibly be an artifact of a specific camera, processing step, or environmental condition? Second, if the signal is real, does it have any implications for spacecraft safety, pointing, or scheduling that require immediate action? Third, how sensitive are the preliminary interpretations to calibration choices and modelling assumptions, and what minimal set of cross-checks will lower that sensitivity? Only after those questions have provisional answers do communications teams draft language that goes beyond "we are reviewing data." Another factor that extends the quiet window is the presence of partner data under separate review processes. Mars missions involve collaborations across centres and institutions. If a short pressurised period of high-cadence imaging has to be vetted by a project's instrument leads before distribution, public commentary that leans on those images must wait for their green light. Similarly, If the best early astrometry comes from a mix of professional and amateur facilities, the agency may choose to cite only the existence of cross-institutional consistency rather than specific numbers until the Minor Planet Center and Orbit determination teams issue consolidated updates. During the first several hours, media liaisons fielded focused questions. Did the Mars orbiters see anything unusual in their own instruments? Did the Deep Space Network schedules shift in response to any instrument modes? Were there any contemporaneous changes in spacecraft health indicators? The provided answers were narrow. Teams confirmed that instrument health remained nominal, that any minor DSN scheduling adjustments were routine load balancing, and that a deliberate pause in interpretation would remain until calibration checks concluded. Reporters and outside commentators sometimes infer more from what is not said than from what is said. In this case, the absence of numbers was not a hint that numbers were alarming, it was a sign that numbers were being double-checked. The next visible phase of the quiet window involved internal tiger team formation. When an event straddles photometry and dynamics, as the 3i Atlas case did with a brightness spike, and a small improvement in trajectory fits, project scientists often gather specialists across disciplines to agree on what to test next. That group defines a minimal set of discriminants. Look for color changes during any future spikes, compare core-weighted and aperture-weighted centroids in real time, schedule deeper spectra at the earliest possible windows, and extend astrometry to see if a transient push remains the preferred fit. While that planning proceeds, public channels remain generic to avoid over-promising on timelines or outcomes. Silence also protects against a well-known pitfall: early model lock-in. If a project's first public statement suggests a specific mechanism, say, event opening and then sealing, later retractions become harder even when new data point elsewhere. For this reason, the first post-quiet statements tend to describe what teams are doing rather than what they think caused the event. This can frustrate audiences seeking definitive answers, but it's the right approach to keep the analysis clean. One common misunderstanding is that no comment implies external pressure to suppress a result. In practice, the gate is almost always internal quality control. Flight projects carry formal review gates for anomaly-like events, whether or not the event is truly an anomaly. Those gates exist to maintain consistency, to protect instrument health while investigations run, and to ensure that public-facing material does not outpace the science. Interagency coordination can add modest delays as well, especially if partner agencies or international collaborators need time to check their own data before joint statements. The end of the quiet window usually coincides with two developments: the availability of additional independent measurements that either confirm or weaken the initial interpretation, and the completion of at least one round of cross-calibration that holds up across pipelines. For 3i Atlas, the practical trigger was the assimilation of enough post-encounter positions to determine whether a brief push truly reduced residuals in that segment without degrading the longer arc fit. In parallel, photometric re-reductions from different teams, using different aperture strategies, continue to recover the same step-like light curve feature across facilities. Once those pieces aligned, communications teams gain the freedom to describe the situation more concretely. An unexpected short-duration brightening observed by multiple instruments, and a small, time-localized improvement in trajectory fits when a brief non-gravitational term is included. From a process standpoint, the quiet window around 3i Atlas lasted long enough to complete the basic checks, but not so long as to impede follow-up. Ground-based observers still received rapid guidance about what data would be most valuable next: tighter astrometry, simultaneous multi-band photometry to test for color stability during any future events, and spectra as early in each window as feasible. Mars-based assets adjusted their monitoring blocks to sample possible delayed changes in the inner haze while protecting onboard resources. The measured return to normal communications coincided with that guidance, signaling that the verification phase had completed its first pass. The core points for viewers tracking this phase are straightforward. The absence of immediate commentary did not indicate instrument failure. It indicated a disciplined use of time to verify a short-lived cross-facility signal before speaking publicly about it. The operational cadence, continuing measurements while pausing interpretation, fits the standard playbook for any event that might hinge on calibration details or on subtle modelling choices, and the resumption of more informative updates aligned with the arrival of independent checks rather than with external pressure. In other words, the quiet was a feature of responsible analysis, not a sign of something being withheld. The image that circulated most widely was a compressed screenshot of a brightness versus time plot, attributed to an observatory that had been running high-cadence photometry through the Mars flyby. At first glance, the trace appeared to show a clean vertical jump at the time of closest approach for 3i Atlas, followed by a rapid decay toward baseline. The vertical axis lacked a clear unit label in several reposted versions. Some readers assumed raw counts, others assumed standardized magnitude. The horizontal axis alternated between absolute timestamps and seconds from event, depending on which crop people shared. These inconsistencies mattered, because a shift from flux to magnitude or from local time to UTC can change how dramatic the same curve appears. Several variants of the graph were actually the same underlying capture, re-exported multiple times. Each re-export introduced small distortions. Anti-aliased fonts became fuzzier, grid lines thickened, and compression blocks formed around sharp transitions. Near the peak, where the slope was steep, those compression artifacts created ringing, little overshoots and undershoots that some posts misread as secondary spikes. In versions where the axes were cropped tightly, the absence of error bars led viewers to interpret a perfectly smooth curve, even though the original included per-point uncertainties that widened during the faintest intervals and narrowed as the target brightened. A careful reading of the original, as described by those who saw it before heavy cropping, indicates the following. The data were binned at a cadence optimized for the expected motion near closest approach. A rolling average was applied for the quicklook display, and the 0 point was tied to an ensemble of comparison stars in the same frame. The event manifests as a step-like rise over a few sampling intervals, a short shoulder, then a monotonic decline. The peak amplitude, expressed by the team in relative flux rather than formal magnitude, translated to a modest but unmistakable increase in brightness. The curve's smoothness in the native plot was a function of binning and the rolling average. The unbinned points, according to observers who worked with the raw list, showed the usual scatter associated with seeing and photon noise. Provenance became the central question. Who produced the graph, with which pipeline, and under what calibration assumptions? The best practice in these situations is to ask 4 things about a light curve before drawing conclusions. First, confirm the time base. Was the horizontal axis UTC, a local offset, or seconds from an internally marked event? Mismatched time bases across instruments can create the illusion of misalignment or conversely agreement where there is none. Second, identify the photometric system. Raw counts, instrumental magnitudes, and calibrated magnitudes tell different stories. Third, verify the treatment of comparison stars. A curve corrected against a single comparison star can inherit that star's variability. An ensemble correction is more robust. Fourth, examine the aperture strategy. Fixed radius apertures behave differently from growth curve approaches when the target's profile changes rapidly. The leaked graph scored mixed marks on these checks when viewed in screenshot form. The time base appeared consistent within the series, but reposts that overprinted T0 markers at slightly incorrect positions introduced confusion. The photometric system label was missing in most crops. Only those who saw the original noted that values were relative flux normalized to a pre-event baseline. The use of multiple comparison stars was not obvious from the screenshot, though later clarifications from observers stated that an ensemble method had been used. The aperture note, fixed in pixel space for the critical window, was legible only in the highest quality version. Interpretation threads split along predictable lines. One camp treated the plot as decisive proof of a physical flare and demanded immediate explanations. Another camp dismissed it as a calibration glitch, pointing to the missing labels and compression artifacts. A small subset proposed non-physical interpretations based on perceived patterns in the noise, steps, or bursts, that appeared only in low-resolution reposts. The responsible approach is to treat the plot as suggestive but incomplete, and to ask whether independent datasets, reduced with different tools, show the same timing and amplitude. Cross-checks began with side-by-side comparisons to other facilities' quicklook curves. Where those curves were available, they showed a feature at the same time, though with different amplitude, consistent with different apertures and seeing. Importantly, at least one observatory reported the same step and decay pattern without applying a rolling average, confirming that smoothing did not create the feature. A second check involved examining the light curves of several nearby field stars in the same frames. Those stars remained flat during the interval, which argued against sky transparency changes or guiding errors creating a false signal. A third check looked at raw counts in the detector's brightest, most linear regime to ensure the peak did not flirt with nonlinearity. The counts stayed within comfortable limits. Another point of confusion involved the graph's vertical scaling. Some reposts inverted the axis, as is customary for magnitudes, while others treated higher as brighter, as is customary for flux. This inversion led to contradictory narratives about whether the object dropped or spiked. The original used flux normalized to unity, where values above 1 indicated brightening. When a magnitude-style inversion was overlaid later by a third party without changing the y-axis label, it created a misleading impression of a dip. In a domain where many viewers straddle amateur and professional practices, such mismatches are common and can derail public interpretation. Compression artifacts deserve more attention because they explain several of the mystery wiggles that proliferated. When a sharp feature is compressed into a small number of pixels, standard image encoders approximate the slope by introducing small, alternating blocks of darker and lighter pixels near edges. On a line plot, those blocks look like tiny pre- and post-echoes. If the screenshot is then recompressed, for instance, by a social platform that resizes images, those artifacts amplify. A reader mistaking them for real substructure might conclude the flare contained micropulses, when the uncompressed data show only a single, clean transition. The file metadata, discussed by those who handled the original export, included the observing site, instrument, filter, exposure time, and an internal reduction tag. While the metadata was stripped or scrambled in many shares, the presence of those tags in the original lends weight to the claim that the curve came from a legitimate quicklook tool, rather than from a third-party mock-up. Even so, quicklook products are not final reductions. They prioritize speed and human readability over rigorous error propagation. That is why teams refrain from quoting exact amplitudes or durations from such plots, until full pipelines, with their traceable calibration steps, reproduce the result. A measured way to use a leaked graph constructively is to ask whether it helps plan better follow-up. In this case, the graph's cadence suggested the flare evolved on the order of several seconds. That has immediate implications. Simultaneous multi-band imaging is more informative than cycling filters. Frame times should be short enough to resolve a sharp rise without saturating, and observers should maintain fixed apertures in pixel space across the expected window to avoid mixing algorithm changes into the light curve. The timing also argued for coordinated coverage at future rotational phases, where a repeat, if geometric, might occur. Another constructive step is to attempt independent reproduction from raw or lightly processed data. Teams with access to their own frame stacks can rederive relative fluxes using an ensemble of comparison stars, test both fixed aperture and growth curve methods, and apply no smoothing beyond binning at the native cadence. If those efforts recover the same feature at the same time, even with different telescopes, filters and skies, that elevates the status of the leaked graph from curiosity to corroborated evidence. Several groups reported exactly this kind of concordance in private updates before any public summary appeared. The social dynamic around the graph deserves acknowledgement because it affects how technical information spreads. Cropped images without context travel farther than annotated, slow-to-load plots. Threads that emphasize mystery attract more engagement than threads that explain image compression or aperture photometry. As a result, a tool meant to give operators a quick sanity check became, in public, a Rorschach test. The best antidote is consistent, plain language from observers about what the plot can and cannot show. It indicates a short-duration brightening. It does not by itself identify the cause. It was generated by a quicklook pipeline, and independent datasets are being compared to confirm timing and amplitude. Several specific misreadings can be laid to rest. The slight double top seen in some reposts was an artifact of the rolling average window crossing a steep feature, not two physical peaks. The apparent pre-flare ramp visible in a heavily contrast-stretched version was a background gradient clipped differently by an image editor, not a physical warm-up. The claim that the flare lasted minutes originated from a graph where the x-axis ticks were mislabeled after a user stretched the image horizontally. The native plot and the raw timestamps show a span of seconds to tens of seconds. And the idea that a signal was embedded in the post-flare noise surfaced from an over-zoomed region where quantization produced a dotted line. The underlying points, at full resolution, show normal scatter. The most important technical takeaway is that the leaked graph, despite its messy public life, aligns with a pattern documented independently. A short, sharp increase in brightness near closest approach for 3i Atlas. That pattern matches what multiple observatories reported through their own pipelines. The precise amplitude and duration will belong to the final reductions, not to a screenshot, but the qualitative shape is consistent. When paired with the small improvement in post-encounter trajectory fits that include a brief push, the case for a genuine, short-lived event is stronger than it would be from either line of evidence alone. As a final practical note, future quick-look products can be made more robust against misinterpretation without slowing operations. Always include unit labels on axes, even in internal tools. Add a small panel with the comparison star ensemble average to show environmental stability. Overlay simple, per-point uncertainty bars or a shaded band to discourage the idea that the curve is exact, and watermark the time base, UTC, seconds from T0, directly on the plot so that crops cannot remove it. These small changes help the community read what matters when inevitably a screenshot escapes the intended audience. In short, the graph that everyone shared should be treated as a pointer, not a proof. It pointed to the right moment, it captured the right general shape, and it galvanized useful scrutiny. Its limitations are typical of quick-look material seen out of context. When interpreted alongside properly reduced, independently acquired datasets, it becomes one tile in a larger mosaic that describes what 3i Atlas did in the seconds after it passed Mars. In the hours around the Mars flyby, several operational cues from Mars orbiters looked different enough that outside observers described them as a blink. This included short, unsignaled gaps in public telemetry mirrors, brief notes about instrument state changes, and schedule shuffles visible to partners that track routine relay passes. On their own, any one of these would be unremarkable. Taken together, they created the impression that spacecraft near Mars paused, reset, or reprioritized just as the 3i Atlas transient was being discussed. For context, a blink in Mars orbiter operations usually means one of three things. First, a pre-planned maintenance window, reaction wheel momentum dumps, brief star tracker recalibrations, or instrument warm restarts that temporarily suspend science. Second, a precautionary configuration change prompted by an onboard autonomy rule. Something reads out a family, temperatures, currents, attitude rates, so the spacecraft powers down non-essential loads and points its arrays at the sun until operators review the data. Third, simple scheduling collisions. The orbiter keeps doing its job, but a ground antenna is reallocated for an hour, and the downlink you normally see moves or goes quiet. All three produce the same surface effect to outside watchers: fewer images, fewer status notes, and a short-lived drop in chatter. Mars Reconnaissance Orbiter is a good example of how routine work can look like a reaction. It carries high-rate images and serves as a major telecom relay, so it regularly cycles between tight pointing for instruments and attitude maneuvers for downlink. When wheels accumulate momentum from continual pointing changes, the spacecraft must fire small thrusters to desaturate them. During that maneuver, science is paused, and telemetry can switch from high-gain, high-rate sessions to lower-rate housekeeping. If a desaturation lands inside a high-interest observing window, it reads to the public as a gap right where curiosity is highest. In the same vein, if a star tracker reports a brief loss of lock, bright limb lights, glints, or unexpected backgrounds can do this. The onboard rules may command a posture that protects power and attitude until the tracker is happy again. That posture prioritizes sun and safety over science, and can defer data until the next ground pass. MAVEN, which studies Mars's upper atmosphere and its interaction with the solar wind, is deliberately conservative around dynamic plasma conditions. Its instruments are designed for the environment, but the spacecraft will still switch instruments into benign states if counts spike, or if attitude rates approach thresholds during a slew. Operators sometimes schedule campaign modes for bow-shot crossings or solar events, then revert to nominal. In logs, these transitions appear as short spells of reduced data volume or different instrument modes, followed by a return to standard sequences. If such a transition brackets the 3i Atlas passage, it can look like a reaction to that event when it is actually a response to space weather or to pre-approved campaign timing. Mars Odyssey is the steady relay workhorse. Its science instrument typically operates at moderate cadence, but its most visible role is as a communications backbone for surface missions. When rover support is prioritized, its schedule can shift to maximize overflight coverage and UHF relay windows, even if that means deferring a planned imaging strip. In practice, that means a timeline that originally allocated daylight science may be reshaped to accommodate relay passes, and the science you expected to see now appears later. To an outside observer building a narrative around a single moment, this benign reprioritization can be misread as an abrupt stop. How does a precautionary mode actually unfold on a Mars orbiter? The pattern is standardized across missions. An autonomy limit trips. The spacecraft automatically powers off non-critical instruments, slows or halts any slews that are not required for power safety, and points its arrays to ensure a healthy energy and thermal balance. Telemetry switches to a robust low-rate configuration that uses antennas with the widest beams and the lowest risk of mispointing. The spacecraft then waits for ground to review the fault summary. On the ground, engineers examine time tags, compare recent currents and temperatures to family plots, and check attitude solutions from star trackers and gyros. If everything is nominal except one spurious sensor excursion or a short-lived tracker dropout, the team uplinks a simple recovery sequence that restores the prior plan. The process might take 1 or 2 ground passes. During that period, the public mirrors that syndicate mission status do not change much, and social updates are often paused by policy to avoid conflicting messages while flight controllers are busy. Short maintenance windows can produce the same external signature without any fault. High-resolution cameras require periodic calibrations, dark frames, flat field checks, focus sweeps, to keep their products consistent over long missions. Spectrometers run gain checks. Telecom subsystems perform receiver calibrations and transmitter power verifications. These are scheduled when geometry is convenient, not necessarily when the public is watching. If momentum management, a calibration, and a downlink handover overlap in time, the resulting lull can appear intentional even when it is just a pile-up of routine tasks. Deep space network scheduling further complicates the picture. Antennas are booked across many missions. If one 34-meter dish is pulled to support an unexpected activity elsewhere, another dish may pick up the slack at a different time or data rate. The spacecraft continues to record science locally, but you will not see those data in the usual near real-time feeds until the next downlink. For outside observers tracking minute-by-minute developments, that delay feels like silence. Internally, it is a normal shift in the ground segment. What about the specific cues people noticed? Maintenance, safe mode, and reprioritization near the 3i Atlas window. Maintenance on a status line is often a placeholder for any scripted pause in science to run housekeeping tasks. Safe mode is a precise term. It indicates a protective configuration that keeps the spacecraft power positive and thermally safe until ground restores full operations. Missions try to avoid using that label casually in public notes unless it truly occurred. Reprioritization usually points to relay obligations. For example, giving a surface mission a better communications geometry, rather than holding an imaging plan that can be retasked later. The key is disentangling correlation from causation. The brightness spike from 3i Atlas happened inside a narrow window. Multiple routine processes also tend to cluster there because closest approach geometry drives everyone to schedule high cadence observations. High cadence means more slews, more data, and more complex sequences, which in turn raise the chances that a momentum dump, a tracker recalibration, or a rate limit guardrail will trigger during the same span. From the outside, that co-occurrence looks coordinated. From the inside, it is simply how risk is managed when you try to do a lot in a short time. One operational detail that often goes unnoticed is how conservatively autonomy rules are written on aging spacecraft. MRO, Odyssey, and MAVEN have all been operating for years. Their teams tighten margins over time, not because the spacecraft are fragile, but because long-lived hardware is valuable, and small surprises can become big ones if left unchecked. A temperature that used to be acceptable as warm but fine might now trigger a cautionary pause until trend analysis confirms it is still benign. Those policy choices produce more short blips that look like pauses to the public, but are really the spacecraft's immune system doing its job. Another source of apparent blinks is ground-side data handling. Near major campaigns, teams sometimes switch to alternate telemetry modes or test patch updates to flight software, commanding, or data compression. These actions are heavily rehearsed and approved in advance, but they still produce short data gaps or different cadence on public mirrors because the ground pipeline is reconfiguring. Engineers can reconstruct and publish the missing slices later, but in the moment it reads like silence. Importantly, nothing about a brief pause in public updates implies that a spacecraft saw or reacted to 3i Atlas. A Mars orbiter's sensors are facing Mars most of the time. When 3i Atlas passed by, only specific instruments in particular modes would have had incidental sensitivity to it. Changes in those instruments' states during the window say more about resource management and flight rules than about external stimuli. That is why official channels avoided narrating the coincidence in real time. It is easy for wording to imply a causal link that the data do not support. When flight teams do suspect a genuine environment-driven effect, say a solar energetic particle event increasing detector backgrounds, they communicate that as an environment note rather than as an anomaly. You might see phrasing like elevated backgrounds, temporary instrument standby, or campaign mode for space weather. By contrast, when the driver is purely operational, notes will reference maintenance, sequencing, or wheel desaturation. The language chosen is a quiet signal about what kind of thing happened without inviting premature physics speculation. For people building timelines after the fact, there are practical checks that help interpret blinks correctly. Look for symmetry. Did a lull occur at nearly the same local solar times on adjacent orbits? That suggests a scheduled activity. Check for accompanying relay notes. If a rover had a high priority downlink, an orbiter may have shifted to support it. Watch for recovery markers. A 1 or 2 orbit return to normal status updates is typical for precautionary configurations. Longer gaps imply deeper investigation, and compare multiple orbiters. If all show lulls in the same hour, the cause is more likely DSN scheduling or a common operational rhythm than simultaneous faults. Finally, it is worth separating spacecraft behaviour from public messaging choices. Communications leads frequently pause social and blog updates, while verification steps run. This is not secrecy. It is a safeguard against confusing the record while controllers confirm health and calibrations. During the 3i Atlas window, that pause overlapped with the most interesting minutes for skywatchers. The result felt like the orbiters blinked in unison. Under the hood, the picture is more mundane, a stack of ordinary activities: momentum management, instrument calibrations, relay reprioritizations, DSN handoffs, and a few cautious autonomy nudges, playing out in the busiest hour of a well-planned campaign. Reports of a faint ring-like enhancement near the orbital distance of Phobos surfaced within hours of the Mars encounter and were quickly labelled a ripple. The observation, as described by multiple teams, was subtle. After aggressive background subtraction around Mars, a low-contrast annulus appeared in stacked images, brightest along a short arc roughly aligned with the Sun-Mars line, its radial position mapped, within uncertainties, to the projected orbital radius of Phobos at the time, while a much weaker, broader glow seemed to sit closer to Deimos's track. The feature was at the edge of detectability, varied with processing choices, and did not appear in all datasets. Because 3i Atlas crossed the Martian neighbourhood minutes earlier, some observers asked whether the two phenomena were connected. The more conservative reading is that several mechanisms, instrumental, environmental, or genuinely dust-related, can produce an annulus at that location, and each must be tested before assigning cause. The first category of tests focused on optical system behaviour. Bright planets generate extended wings in the point spread function, and a family of internal reflections inside camera optics and filters. These effects often manifest as rings or arcs at fixed radii in pixel space, not sky space. Teams therefore rotated the field between exposures and restacked. An optical ghost tied to the instrument rotates with the camera. A sky-fixed structure remains aligned with Mars. In several sequences where the camera position angle changed by tens of degrees, the annulus remained locked to Mars-centered sky coordinates rather than to detector coordinates, arguing against the simplest ghost hypothesis. However, the possibility of out-of-field stray light, scattering from Mars just outside the frame, could still produce a Mars-centered ring that is instrument-specific. To probe that, observers compared stacks taken with different baffling, filters and focus offsets. The ripple's visibility changed with filter band and baffling quality, more than would be expected for a truly astronomical structure, a point that keeps the instrumental explanation in play. Background handling was the second lever. Around a bright planet, the sky is not flat. There is a smooth gradient from scattered light and, in some filters, faint atmospheric emission lines. Subtracting that background involves fitting a low-order surface and masking stars, moons, and the planet's saturated core. If the fit is too aggressive or the mask too tight, the subtraction can carve a false ring at the radius where the background model transitions from over to under fit. Teams ran control stacks with different polynomial orders, mask sizes, and robust estimators. In the stricter reductions, the annulus persisted but with reduced contrast. In the most aggressive, it vanished alongside known, real features such as Phobos itself when present in the frame. That behaviour suggested the ring, if real, had a surface brightness close to the modelling floor. A third diagnostic was azimuthal averaging. After masking stars and known artefacts, analysts computed the median brightness as a function of distance from Mars. A bump appeared near the Phobos radius in some datasets, but its significance depended strongly on how the inner region was masked and on whether unsharp masking had been applied earlier. Unsharp masking, intended to highlight local contrasts, can imprint artificial ripples around steep gradients, exactly the context near a bright planet. In stacks where only gentle, large-scale background removal was applied and no sharpening used, the radial bump was weaker but not eliminated, keeping the case ambiguous. Colour and polarization offer additional discriminants. A true dust ring sourced by meteoroid impacts on Phobos would likely show a colour slope close to that of other Martian dust populations and exhibit some degree of polarization that varies with phase angle. Instrument ghosts, by contrast, are largely achromatic within a filter and unpolarized. The available data included limited multi-band coverage and essentially no polarimetry. Where two filters were used nearly simultaneously, the annulus's contrast did not change strongly with wavelength, but the uncertainties were large. That result neither confirms nor rules out dust. It does, however, suggest that future attempts should prioritize strictly simultaneous dual-band imaging, and, if feasible, simple two-angle polarimetry to separate real scattering from optical scatter. On the real phenomenon side, two physical sources are plausible: a tenuous dust torus seeded by Phobos and Deimos, and a transient enhancement in forward scattering from charged grains, responding to the local plasma environment. Micrometeoroid impacts on small moons are known to eject fine particles at speeds below escape from Mars. Those grains can populate ring-like tori near the moon's orbits on timescales of hours to days, before being swept away by radiation forces, plasma drag, or re-impact. The expected surface brightness is extremely low, explaining why detections have been elusive. Forward scattering peaks at specific sun-target observer geometries. During the 3i Atlas window, the phase angles were favourable enough that any existing torus could brighten by a modest factor. That scenario produces an annulus centred at the moon's orbital radius that persists irrespective of 3i Atlas, and would be most visible along solar-aligned arcs where scattering is strongest. The plasma interaction idea connects more directly to timing. As Mars's bow shock and patchy magnetic crust interact with the solar wind, the local electric fields can vary on short timescales, changing the charging state and dynamics of submicron grains. A brief change in charge environment could alter the vertical thickness and local density of a dust torus, making a ring appear or brighten for minutes before dissipating. That mechanism naturally produces transience and alignment with solar wind conditions rather than with any one object's passage. It also predicts that in situ, plasma data near Mars would show a coincident shift, and that the effect would be more pronounced for the smallest grains, potentially yielding a colour dependence skewed towards shorter wavelengths. The most speculative link, 3i Atlas directly causing a ring, has the weakest support. The amount of material that the object could plausibly contribute during a few seconds of activity is minuscule compared with even a tenuous moon-sourced torus, and the geometry is not favourable for depositing dust into circular orbits near Phobos. Any material released would follow the object's hyperbolic path or be swept into heliocentric trajectories. Capture into a narrow annulus at the moon's orbital distance would require fine-tuned conditions. A more defensible connection is indirect. The presence of a bright transient drew intense, Mars-centered imaging at just the moment when a pre-existing marginal ring was easiest to see. In other words, correlation through observation density rather than causation through physics. Independent checks came from datasets that did not include 3i Atlas at all. Several teams pulled archival stacks of Mars at similar phase angles and instrument setups from prior apparitions to test whether a Phobos radius bump appears under comparable conditions. In some archives, a barely significant annulus can be teased out with the same processing steps, hinting that the feature might be a persistent low-level dust torus rather than a unique event-linked ripple. In others, no such bump emerges above noise, underscoring how close to the detection threshold these analyses operate and how sensitive the results are to instrument scatter and background modelling. A practical technique borrowed from high-contrast exoplanet imaging helped. Rotational differential imaging replaces the planet's glare with a reference built from a library of similar point spread functions, then subtracts it before searching for faint co-rotating structures. Applied here, a PSF library constructed from Mars images at slightly different position angles reduced the extended wings and ghosts, and the residuals were searched for ring-like enhancements. Where the library was a good match, the annulus near Phobos persisted at low significance. Where the match was poor, subtraction residuals drowned any subtle structures. This approach shows promise but demands a much larger library and careful control of colour and focus differences between library and target frames. Time domain behaviour was another clue. If the annulus traces dust physically associated with Phobos, its azimuthal brightness should modulate with the moon's orbital motion and with changing phase angle during a night. Short arcs of enhanced brightness could drift slowly with the moon's true anomaly. In the limited sequences acquired, any such drift was below confident detectability. The bright arc's orientation did track the Sun-Mars line, but that is consistent with both forward scattering by real dust and with certain families of instrument scatter that depend on where the bright source sits relative to the optics. Longer, uninterrupted runs will be needed to test for orbital modulation. On the Deimos side, the evidence was even thinner. A broader, lower contrast glow at larger radius that could as easily be the tail of the background model as a genuine torus. Because Deimos is smaller and ejector yields are likely lower, any dust torus there should be fainter. Few datasets reached the depth required to say more than that nothing obvious stood out beyond the Phobos radius. Several guardrails emerged from the combined analyses. First, avoid unsharp masking when the science goal is to detect smooth, extended structures around bright planets. It creates ripples that mimic the target. Second, always perform the position angle rotation test to separate camera-fixed from sky-fixed features. Third, include at least one strictly simultaneous two-band sequence. Even coarse colour information helps sort dust from optics. Fourth, if possible, add a simple polarimetric check. Real dust will show a polarization signature that ghosts lack. Fifth, build and share a PSF library for Mars in each filter and camera configuration so that future attempts do not start from scratch. From a communication standpoint, it was tempting to present the annulus as a dramatic new structure linked to the 3i Atlas event. The more accurate framing is narrower. Some teams, under certain reductions, recovered a low-contrast, Mars-centered ring-like enhancement near the Phobos orbital radius during the encounter window. Similar hints exist in carefully treated archival data. The balance of evidence allows but does not require a real dust torus, and no mechanism tied directly to 3i Atlas is needed to explain the observation. The best near-term path to clarity is a dedicated multi-night campaign on Mars at favourable phase angles, with coordinated processing protocols and explicit instrument scatter control to determine whether a Phobos dust torus can be characterised consistently and whether any transient brightening correlates with space weather conditions rather than with the passage of an interstellar object. In operational terms, this episode nevertheless shaped follow-up. Imaging scripts for subsequent nights added standardized background sampling away from Mars to improve gradient fits. Observers allocated small blocks for fixed angle and rotated angle pairs to run the ghost test automatically. Teams coordinated to obtain short simultaneous dual-band sequences and to share raw frames so that independent pipelines could probe the same data for or against the annulus. Mars orbiter teams reviewed whether any scattered light monitors or limb imagers gathered data that might indirectly constrain dust close to the moon's orbits, even if their instruments were not designed for ring detection. Those steps turn a marginal processing-sensitive hint into a defined experiment. The provisional takeaway is that small Martian moons can imprint subtle, extended structures that are easy to confuse with optical effects and background modelling artifacts, and that any claim of a ripple near Phobos must pass a higher bar than a single stacked image with aggressive subtraction. The encounter with 3i Atlas provided motivation and geometry, but the existence and properties of such a ring, if present, rest on Mars and its moons, not on the visitor. The expected behaviour for a small body's tail near Mars is straightforward in first order. Dust features align roughly opposite the Sun as radiation pressure and the object's motion shape their curvature, while ion features tend to trace the local interplanetary magnetic field carried by the solar wind, producing a narrower, straighter structure that swivels as space weather changes. What observers documented around the 3i Atlas pass did not fully match these expectations. In stacked images from multiple sites, the dominant extension did not consistently point along the simple anti-solar vector. Short arcs appeared to kink, rotate, or even momentarily lean toward Mars before relaxing back toward the nominal direction. The deviations were small in angle, but persistent enough across reductions that analysts treated them as real until proven otherwise. The first step was to separate dust-dominated from gas-dominated structures. Broadband images emphasize dust. Narrowband filters and low-resolution spectra can isolate the principal ion emissions. Where two filters were used in close succession, the narrow bluish extension expected from ions was either absent or weak, while a broader, slightly redder fan was consistently present. That balance points to a dust-heavy feature. Yet dust tails do not pivot quickly unless the ejection geometry changes or projection effects are strong. To test projection, teams reconstructed the viewing geometry through the window. Phase angle was moderate, and the line of sight to Mars put 3i Atlas against a background with rapidly changing geometry, which can exaggerate apparent rotations when a curved structure is seen at an angle. Simulated overlays using standard dust dynamics predicted a gentle sweep, not the sharper kinks seen in a subset of frames, suggesting additional factors were at work. One candidate is multi-jet activity tied to rotation. If 3i Atlas emitted dust from two or more active areas, each jet would lay down particles with different launch directions. As the body rotated, the dominant stream could switch, producing a tail that appears to swivel on short timescales. Analysts looked for period link signatures by phasing the apparent tail angle against candidate rotation periods derived from earlier light curves. The match was inconclusive. Intervals of apparent alignment alternated with windows showing no clear phase relation. This suggests rotation may contribute but is not the whole story. A second mechanism involves the size distribution of emitted grains. Large, relatively compact particles respond weakly to radiation pressure and remain closer to the object's orbital path, while smaller grains are pushed more strongly anti-sunward. If an outburst briefly favoured larger grains, such as a crust flake breaking down into millimetre to submillimetre fragments, the visible tail could lean away from the canonical anti-solar direction, and then gradually transition as smaller grains dominate again. Brightness profiles along the feature were consistent with a population that included unusually large grains relative to low-activity comets at similar distances. The surface brightness fall-off was shallow near the body and steepened farther out, a pattern compatible with a mix evolving towards smaller sizes with distance. That profile does not by itself prove large grains, but it supports the scenario. A third possibility is a transient in the solar wind that altered the local magnetic field direction or strength, briefly tugging any ionized component into a different orientation, and, through charging and Coulomb drag, influencing the smallest dust grains embedded in the flow. The knot of disturbed field lines around Mars, its induced magnetosphere and bow shock, adds complexity. Grains near the charging threshold can flip charge states, changing how they couple to the electric and magnetic fields. In this picture, a short-lived field rotation or density change would bend the finest dust in any nascent ion tail, superimposing a subtle kink onto a dust-dominated structure. Because the ion signature was weak, this explanation relies on charged dust dynamics rather than a bright plasma tail, which is difficult to confirm without in situ measurements. Still, the timing, closest approach to Mars where bow shock effects are strongest, keeps this avenue plausible. Projection effects can easily masquerade as twists. When the observer's line of sight crosses the object's orbital plane, certain dust features that are physically anti-solar project as sunward-pointing anti-tails or as tilted fans. Neckline structures, formed when grains released at an earlier epoch reconverge along the orbital plane, can produce narrow enhancements that slice across the broader tail at curious angles. Analysts therefore generated plane-crossing timelines to see whether the observing geometry favoured such illusions. The geometry was not at the classic high-impact crossing angle for a strong anti-tail, but it was close enough that weaker projection features could appear. This helps explain mild misalignments, but does not fully account for the apparent time variability unless the structure being projected changed rapidly, which brings the analysis back to rotation or a transient emission episode. Instrument and processing artifacts were examined in parallel. Unsharp masking and aggressive background subtraction can create radial streaks or apparent bends where gradients change sign. To guard against that, teams compared minimally processed stacks, only flat-fielded and bias-corrected with gentle background modelling, to heavily enhanced versions. The kink persisted in conservative reductions, though at lower contrast, and its position angle shifted smoothly over adjacent frames rather than snapping with processing choices. That behaviour points away from pure reduction artifacts. Additionally, position angle rotation tests, reframing the field with different camera angles, showed the feature remaining fixed on the sky rather than on the detector, further reducing the likelihood of an optical ghost. A useful diagnostic came from measuring isophote shapes, contours of equal brightness, close to the nucleus. In a simple, single-jet dust fan, inner isophotes elongate smoothly along the jet axis. In the 3i Atlas data, inner contours were slightly skewed relative to the outer tail axis during the intervals when the kink was most pronounced. That skew indicates a local emission direction that differed from the large-scale tail orientation, supporting the idea of multiple concurrent dust streams or a rapid shift in the dominant source region. Importantly, the skew relaxed toward alignment later in the sequence, consistent with either the rotation of the source region or the filtering of grain sizes with distance. Spectral context, although limited, contributed constraints. Where low-resolution spectra were obtained close to the event, the continuum dominated and gas bands were weak or absent at the achieved sensitivity. A dust continuum with minimal gas emission is consistent with a tail whose morphology is driven by particle dynamics rather than by an ion flow that would strongly track magnetic field lines. If gas was present only briefly during the earlier brightness spike, by the time the tail images were captured its optical signature may have faded, leaving dust as the main tracer. Comparisons to established dust dynamics models highlighted the mismatch. Standard Sindine synchrone maps, curves that trace where grains of a given size released at a given time should lie, predicted a fan broader on one side tightening toward the anti-solar direction with distance. The observed feature cut across several of these predicted curves in a way that implied either a sharp change in ejection direction within minutes, or an injection of grains with sizes not sampled in the baseline assumptions. When the maps were regenerated with a bias toward larger grains and with a transient jet, oriented slightly off the sunward hemisphere, the fit improved, producing a gently canted fan for a short time that then relaxed toward the nominal direction as smaller, freshly released grains took over. The proximity to Mars raises another consideration. Background contamination and scattered light can bias tail angle measurements, especially when the tail passes over faint residuals from planetary subtraction. To address this, teams measured the tail angle at multiple radial distances from the nucleus and discarded segments where the local background variance was high. The remaining angle measurements still showed a systematic offset of a few degrees from the antisolar direction during the peak interval, decreasing toward nominal over tens of minutes. That trend, offset followed by relaxation, supports a transient driver rather than a persistent modelling issue. One scenario ties the tail behaviour directly to the earlier brightness surge. If the flare was a compact venting episode, it could have launched a short-lived pulse of relatively large particles in a slightly oblique direction. As those grains separated from the nucleus, their higher inertia made them slow to align with the anti-solar direction, imprinting a bent segment that straightened only as smaller grains and later emission, more tightly controlled by radiation pressure, filled in. In this picture, the kink is a time of flight effect, written into the tail by a pulse of unusual material, not a continuing property of the source. Another scenario puts space weather in the lead. A short rotation in the local magnetic field, such as one associated with a sector boundary crossing, can cause an ion disconnection event, severing and redirecting ionized flow. Even if the ion tail was faint, charged dust grains embedded in or near that flow would experience a temporary change in direction, imprinting a bend or lateral offset that would gradually wash out as neutral dynamics reasserted control. The weakness of this explanation is the lack of a strong ion tracer in the data. It remains plausible but unconfirmed without independent field measurements. To sharpen the diagnosis, observers outlined specific follow-up tests. Simultaneous dual-band imaging separates dust and ion contributions in time-resolved fashion, preventing filter cycling delays from smearing short changes. Polarimetry, even at two angles, can differentiate dust populations and identify regions where grain alignment or size distributions shift. Rapid cadence sequences with fixed conservative processing allow the tail angle to be tracked frame by frame without introducing algorithm-induced swing. Finally, coordinated observations at multiple longitudes reduce gaps and allow true temporal evolution to be separated from projection changes as geometry evolves. The practical implications for prediction are modest but important. Short-term tail direction forecasts near planetary encounters should include contingencies for rotation-driven jet switching and for space weather deviations from the smooth anti-solar assumption. For scheduling, that means keeping some flexibility in pointing and framing to accommodate a few degrees of unexpected swing, and for analysis, it means generating multiple families of synthetic overlays, one with a single sunward jet, one with a canted jet, and one with a brief large grain pulse, so that measured angles have immediate contexts. In terms of communication, phrasing matters. Describing the feature as a tail that didn't behave is an accurate shorthand for a nuanced situation, a mostly dust-driven extension that deviated from the simple model by a few degrees for a short period, likely due to a combination of transient emission geometry, grain size effects, and local environment. Framed this way, the observation becomes a useful constraint on how quickly small bodies can change the direction and character of their dust outflow under rapidly evolving conditions, rather than an implication of exotic physics. As the object receded and geometry slowed, subsequent images showed the extension settling into the expected anti-solar orientation, with a curvature consistent with standard dust dynamics. That return to nominal supports the idea that a brief, time-limited disturbance, emission geometry, grain size pulse, or local field variation was responsible for the earlier misalignment. Continued monitoring, especially during any future activity pulses tied to rotation, remains essential for determining which of the proposed drivers best matches the data from 3i Atlas. Amateur and community observatories became the primary source of timely measurements within minutes of the Mars passage, because they could change plans instantly and aim at 3i Atlas without waiting for internal reviews. The first contribution was continuous astrometry, Small and mid-sized telescopes running non-sidereal tracking delivered position measurements at short intervals, each tied to precise UTC stamps synced by GPS-disciplined clocks or well-maintained NTP servers. Observers used modern star catalogues to minimize catalogue-related systematics, reported seeing and sky transparency for every frame, and included full metadata so orbit analysts could weight the measurements appropriately. The density of these positions on both sides of closest approach made it possible to test whether a brief non-gravitational push improved the fit immediately after the event. Photometry from the community provided a second line of evidence. Teams standardized on fixed apertures in pixel space for the critical minutes, kept Skianuli consistent within each block, and reported both differential and absolute results when standards were available. Many observers ran paired sequences, one in a luminance or clear filter for cadence, and one in a red or green filter for color checks. Where instruments allowed, simultaneous dual camera rigs captured independent bands without filter cycling. The collective result was a set of light curves that, despite differences in equipment and sky quality, showed the same step-like increase and rapid return toward baseline during the window around closest approach. Coordination happened in parallel threads across mailing lists, chat servers, and private forums used by photometry and astrometry groups. Volunteers posted their most recent ephemerids, tracking rates, and finder charts with cautionary notes about star crowding and background gradients near Mars. Those in better weather passed the baton to sites facing clouds or twilight, and longitudes were leveraged to reduce gaps. A simple tagging scheme, site code, start time, filter, exposure, seeing, let analysts merge datasets quickly without guessing at context. This exchange replaced speculation with practical guidance. Who had the clearer sky? Who could run short exposures without saturating? And who could provide deeper sequences to tighten positions as the apparent rate slowed? Quality control was explicit. Before posting numbers, teams ran internal checks, linearity tests on the detectors to ensure peaks stayed within calibrated ranges, cosmic ray rejection validated by stacked control frames, and centroid comparisons using point spread function fits versus simpler Gaussian fits to catch any coma-driven centroid shifts. When discrepancies appeared between methods, the measurement was flagged rather than forced into consensus. Observers also compared the behavior of nearby field stars to detect residual transparency variations or guiding issues. A light curve or astrometric point that correlated with field star instability was downweighted or withheld. Several groups adopted a simple shared protocol for validating the transient. First, reproduce the timing. Does a brightness step appear within a few seconds of the same moment when measured against UTC? Second, verify neutrality. Does the feature appear with similar amplitude across common broadband filters after accounting for throughput differences? Third, check centroid stability. Do core-weighted and aperture-weighted centroids agree at the level required for orbit fitting? Fourth, confirm persistence under alternate reductions. Does the step remain when background estimation, aperture size, or cosmic ray thresholds are changed within reasonable bounds? Only when 4 checks passed did teams publish the segment as validated, with raw and reduced files attached. The choice of comparison stars was standardized to reduce color term errors. Observers selected small ensembles close to the target on the detector, avoided saturated stars, and preferred colors that bracketed the expected color of the target. This practice lessened the chance that a flare in 3i Atlas would be mimicked by a comparison star artifact. When observers lacked ideal ensembles, they reported the exact stars used and provided a short note on why the selection was unavoidable, allowing downstream analysts to assess sensitivity to color terms. Trailing and seeing were managed proactively. Near closest approach, exposures were shortened to keep the target's image compact, while maintaining enough signal to avoid purely noise-dominated photometry. For sites with fast readouts, A burst mode captured many short frames that were later aligned on the moving target and stacked for signal. This approach preserved temporal resolution, while improving depth for both photometry and centroiding. Where seeing fluctuated quickly, observers recorded a seeing metric frame by frame to help analysts model how much of a measured flux change could plausibly be due to point spread variations rather than astrophysical effects. Spectral coverage from amateur-friendly spectrographs was limited but not absent. A few observers ran low-resolution spectra with wide slits to avoid slit loss changes during fast tracking. These spectra prioritize continuum behavior and the strongest expected gas features. Even when features were not detected at useful significance, the resulting upper limits were valuable, constraining how much gas could have been present by the time observations resumed after the flare. Data packaging mattered as much as data collection. Contributors uploaded raw FITS frames, corresponding calibration frames, and minimal human-readable logs documenting weather, transparency, and any deviations from plans. Reduced products were provided alongside the raw stacks with full parameter listings. Aperture sizes, ski annulus radii, background model choices, and any smoothing or binning steps. Orbit analysts could then select the most conservative reductions for fitting, while photometrists could compare independent pipelines on the same inputs. A practical advantage of the community response was agility. When early indications suggested that a brief transverse impulse might improve the immediate post-event orbit fit, several teams switched from single long exposures to sequences optimized for positional precision, tighter plate scales where possible, careful selection of reference stars across the field to minimize distortion, and exposures timed to bracket predicted geometry changes. This agility extended to follow-up triage. As soon as a handful of observers recovered consistent timing for the transient, others shifted effort to test for rotation-linked repetition, building schedules around candidate periods proposed from early light curve work. False positive control was explicit in the network's traffic. Observers posted examples of how aggressive background subtraction around Mars could create rings and arcs, shared side-by-side stacks showing the effect of unsharp masking on faint fans, and flagged pixel space ghosts that track the detector rather than the sky. These shared pitfalls reduced the rate at which processing artifacts were misinterpreted as real features and kept the focus on measurements that survived conservative treatment. The community also closed practical gaps left by professional scheduling constraints. While spacecraft teams at Mars followed their approved plans and major observatories cycled through pre-booked programs, small observatories stayed on target for hours beyond the peak window, capturing the relaxation of the light curve and the settling of the tail back toward the anti-solar direction. Those long, quieter sequences were crucial for confirming that the anomaly was time-limited rather than the start of sustained activity. Astrometric submissions benefited from redundancy. Multiple sites measured the same short segments minutes apart, allowing orbit fitters to compare residual patterns station by station. Where one station's residuals showed a systematic bias, caused for example by mild trailing or by reference star selection, another station's clean points kept the fit stable. This redundancy increased confidence that any improvement from a brief non-gravitational term was not the result of one observer's systematics. Rotation studies drew heavily on the community's ability to collect long continuous light curves. Small variations on the order of a few % were tracked across many hours by defocusing slightly to spread the light over more pixels and reduce scintillation noise, a technique well known in exoplanet and asteroid work. These sequences helped test whether the timing of the flare lined up with a specific rotational phase, guiding the scheduling of future checks at predicted repeats of the geometry. Even when no repeat flare appeared, the rotation constraints reduced the space of plausible surface and activity models. Communication from the network emphasized conservative language. Posts avoided causal claims, stating instead that a short-duration brightening was observed at consistent times and that a small improvement in immediate post-encounter trajectory fits appeared when a brief push was allowed. Suggested interpretations were listed in order of simplicity: a compact eventing episode, a geometric reflection with no push, a microfragmentation shedding event, or, less likely, an environment-driven effect near Mars. This framing kept the emphasis on what the measurements could support directly, and what needed more data. Practical guidance for latecomers was distilled into a short checklist that circulated widely. Use UTC and include absolute start and mid-exposure times in headers. Avoid filter changes during predicted windows. Keep apertures fixed in pixel space for the high cadence blocks. Report seeing and background levels per frame. Provide both core-weighted and aperture-weighted centroids. And, if possible, pair a clear or luminance sequence with a red or green sequence taken simultaneously, not sequentially. Observers who joined mid-campaign could follow the checklist and produce data that merged seamlessly with early contributions. Remote access telescope networks played a role by opening slots for rapid requests. Users booked short runs at different longitudes to cover gaps and shared their raw outputs with the same metadata conventions used by backyard and campus observatories. Although these systems vary in calibration quality, the uniform packaging and immediate sharing allowed others to re-reduce the data and extract consistent results. As the object receded and the urgency eased, the community's datasets fed directly into higher fidelity reductions by professional teams. Because amateurs had preserved raw frames and calibration files and documented their choices, analysts could recompute measurements under uniform assumptions, improving consistency across instruments. In several cases, the re-reductions changed individual amplitudes or positions slightly, but left the key findings intact. The timing of the brightness increase clustered within the same seconds, and the small time-localized improvement in fit persisted for the immediate post-encounter segment. The most important outcome of the community effort was not a single dramatic image or plot. It was the conversion of a short, ambiguous moment into a set of cross-checked measurements that others could test and extend. By maintaining cadence through the peak, reporting methods transparently, and coordinating across longitudes, amateurs and small observatories supplied the continuous coverage that made it possible to separate an astrophysical transient from instrument quirks, and to quantify how 3i Atlas behaved as it left the Martian neighbourhood. Whisper mode is an informal description of how the deep space communications picture looked in the hours around the Mars pass. Downlinks that normally appear at predictable times were shortened, moved, or reduced in rate. Antennas that had been earmarked for high-rate returns showed lower-rate engineering sessions instead, and a few frequency retunes appeared mid-pass. None of this requires an extraordinary explanation, but the timing, overlapping the transient brightening from 3i Atlas, meant routine adjustments were read as deliberate quieting. The Deep Space Network allocates time in blocks across 3 complexes, Goldstone, Madrid and Canberra, balancing dozens of spacecraft. Every pass is a compromise among antenna availability, elevation angle, weather, and what each mission needs at that moment: high-rate science playback, low-rate housekeeping, a 2-way coherent track for navigation, or just a carrier for health monitoring. Around the Mars flyby, several things lined up that naturally push operations toward conservative settings. Geometry changed fast. Mars rose or set at awkward local times for at least one complex, and other users of the network had pre-booked windows that could not be moved. The result was a pattern of short sessions, handovers between antennas, and rate changes that from the outside looked like the network had gone quiet on purpose. 2 technical drivers explain most of the rate shifts. The first is frequency and weather. K-band delivers high data rates but is more sensitive to atmospheric moisture. X-band is slower but robust. If a K-band session meets marginal conditions or low elevation, controllers can retune to X-band, drop the modulation index and lengthen the coding, sacrificing throughput to increase margin. That shows up as a pass that starts at one frequency and continues at another, or as a visible downrate mid-session. The second is antenna geometry. At low elevation, link budgets shrink. You accept a lower rate to stay well inside the margin. When a pass straddles low elevations, common when you're trying to cover a narrow window near closest approach, sessions look like they've gone to a whisper, even though the spacecraft is healthy and recording at full speed on board. Scheduling slips are also common when the DSN resolves conflicting priorities. A Mars orbiter might yield a half hour of prime time if another mission has an unplanned activity, or if a navigation track for a time-critical maneuver elsewhere cannot be moved. From the public vantage point, you see a session nudged later, shortened, or split across two antennas. Internally, the orbiter simply holds its science in solid-state recorders and dumps it at the next opportunity. That store and forward architecture is why a lull in downlinks is not the same as a lull in measurements. It only means playback shifts on the calendar. The phrase frequency changes can also reflect perfectly ordinary housekeeping. Ground stations will relock carriers after brief weather-related fades, swap polarization to optimize the link, or change receivers to bring a cleaner chain online. A line in the log that a feed or receiver changed mid-pass sounds dramatic. In practice, it is routine link maintenance. If you layer that on top of a handover, from one 34-meter antenna to another, or from a 34-meter to a 70-meter for margin, you get a pass that, to an outside tracker, looks chopped and quiet. Observers watching public dashboards saw scheduled downlink slip and inferred that the network had throttled communications because of 3i Atlas. The more likely reasons are mundane: a tight turnaround between users, a momentum dump or instrument calibration on a Mars orbiter that shaved the start of a pass, or a rain cell passing over a K-band site that pushed traffic onto X-band at lower rate. The DSN's job is to keep margins healthy. If that means dropping to engineering rates for a while and holding science for the next clear window, controllers will do it without fanfare. Navigation requirements further complicate the picture. Near key events, projects often request two-way coherent tracks to tighten Doppler and range data. Those tracks consume antenna time but deliver little visible product to the public during the pass. The science playback happens later. A day that emphasizes navigation support reads like a whisper. Plenty of carrier, not much news. If a pass flips from playback to two-way mid-session, because a project wants fresh radiometrics right after an anomaly, your external timeline shows a rate drop exactly where curiosity is highest. Arraying adds another wrinkle. To recover margin under less than ideal conditions, controllers can combine two or more 34-meter antennas on receive. That helps the link, but it also ties up multiple dishes and limits who else can transmit nearby to avoid interference. Arrayed sessions are often shorter and more carefully delimited, which again looks like smaller, quieter blocks on public schedules. They are a sign of prudence, not of suppression. Conflicting priorities, the phrase you sometimes see in engineering notes, rarely hides drama. The DSN supports not just Mars orbiters, but also spacecraft at the Sun-Earth Lagrange points, lunar assets, solar probes, outer planet missions, and radar campaigns. If a critical activity for any of those slips, an orbiter playback can be bumped hours with minimal scientific loss. During the 3i Atlas window, the priority stack likely shifted several times for normal reasons. A navigation track elsewhere, a weather-related rate cap, or an internal calibration that could not be moved. Each shift carved small gaps and created the patchwork cadence that outside watchers called whisper mode. It is important to separate ground behavior from spacecraft health. Nothing about a lower rate session implies that a Mars orbiter is in trouble. In a cautious posture, projects will even request low-rate engineering passes on purpose to keep link margins large while they confirm instrument settings or check attitude telemetry. A day of low-rate passes can happen with the spacecraft pointing perfectly, acquiring images at full cadence, and filling its recorder as planned for playback later. That distinction Quiet on the ground, busy in space, is easy to miss when you're building a narrative around a real-time plot. Speculation grows in the gaps between what the network shows and what mission channels say. Around 3i Atlas, official feeds were slow to interpret the photometric transient, so the absence of high-rate playbacks and the presence of retunes was stitched into a story of deliberate hush. The operational record supports simpler explanations. K-band weather, low elevation, antenna handovers, navigation sessions and time-sharing create exactly the pattern that was observed. When those factors stack up during high-interest hour, the appearance of whisper mode is inevitable. For completeness, there are a few edge cases that can look similar but still be benign. If a Mars orbiter hits an autonomy guardrail and pauses science for a momentum dump or a star tracker recalibration, it may also adjust its downlink plan to match a temporary power or pointing constraint. Publicly, you see a shortened session and fewer science packets that day. Within a pass or two, the schedule returns to normal, and the recorder empties during a long, stable contact. Likewise, if a ground antenna undergoes maintenance, feed temperature excursions, cryosystem checks, or a front-end swap, the associated pass can be turned into a low-rate health check or moved entirely. These choices are about protecting hardware and link quality, not hiding data. Frequency agility during the window also served a radio environment purpose. Mars was at a geometry where solar elongation for at least one complex was less than ideal. The Sun's radio noise rises as the angle decreases. Retuning and lowering rates helped maintain carrier lock and telemetry integrity under those conditions. If you are looking at a public spectrum line that shows a move from one band to another, that is usually the explanation. Keep the bit error rate low, then dump the recorder later at a friendlier angle. A practical mapping of the gaps looks like this when you reconstruct it from observer reports. Before closest approach, a healthy, high-rate playback and a two-way track bracketed by standard housekeeping. Around closest approach, one short session drops to a lower rate midway, possibly switches band and ends early for a handover. The next complex picks up with a low-rate engineering pass, then a navigation carrier. Several hours later, a long high-rate block appears and the backlog begins draining. The quiet center is about link margin and scheduling, not about turning off information. For those planning observations key to DSN behavior, the takeaway is to treat quiet passes as normal around tight geometry. Do not assume real-time data will confirm an optical transient within minutes. Assume recorder playbacks will carry the story several hours later. When a pass oscillates between bands or rates, the conservative reading is that controllers are buying margin, not signaling a problem. And when a schedule cites conflicting priorities, read it as the network doing what it always does, balancing many spacecraft, all of them important to someone, over 3 complexes and imperfect skies. Against that operational backdrop, the appearance of whisper mode during the 3i Atlas window did not add new physical information about the object. It added context about how deep space communications adapt under load. The network behaved the way it is designed to behave, protect the link, share the antennas, prefer margin over throughput when conditions are tight, and move the big science playbacks to the next stable block. The coincidence with a high-interest optical event is exactly that. A coincidence amplified by understandable public attention. The small deflection inferred after the Mars pass can be framed in 2 ways that lead to very different stories. In one, 3i Atlas experienced a brief physical event, most plausibly a compact jet or shedding episode, that imparted a tiny push and left a measurable fingerprint in the immediate post-encounter astrometry. In the other, the appearance of a course correction is a byproduct of denser measurements, changing geometry, and subtle centering biases that coincide around closest approach and temporarily favour a model with an extra term. Disentangling those possibilities requires treating the fit as an experiment. Define what changes when a short-lived acceleration is allowed, test whether those changes persist as the tracking arc grows, and look for independent signatures that live outside a single model choice. The baseline for comparison is the pre-encounter solution assembled from days of observations. that solution predicts where 3i Atlas should appear in each field to within the scatter set by plate scale, seeing, and star catalogue limits. Around closest approach, the observing cadence increases and the geometry changes quickly, so residuals, the tiny differences between where the model says the object will be and where it is measured, become an especially sensitive diagnostic. Immediately after the brightness spike, those residuals showed a small coherent pattern that did not look like random noise. When teams permitted a brief transverse push centered on the encounter, the pattern relaxed and the points sat closer to the model. That is the factual core of the course correction claim. Before accepting a physical impulse, orbit analysts ask whether the same improvement could arise from data handling. A common culprit is photocenter drift. If the inner haze around the nucleus brightened asymmetrically during the flare, centroids measured with large apertures can shift slightly away from the true center, even if the body's path did not change. The countermeasure is to compare positions derived from the sharp core of the point spread function to positions derived from larger, flux-weighted apertures. In the encounter data, those two methods tracked each other closely within uncertainties, which lowers the chance that an apparent path change is just a moving photocenter. Another check is station-to-station consistency. If only one site reports residuals that favour a push, it smells like a local systematic. If several independent sites report the same pattern at the same time, local effects are less likely to be at fault. During the Mars window, multiple stations contributed, and the improvement from a brief push was not confined to a single observer. A different class of false positive involves how much weight the fitting software gives to the flurry of high cadence points. If a handful of seconds-long measurements are given disproportionate influence, they can drive the solution toward an extra term that makes those points look better while having no physical meaning. Robust weighting mitigates this by down-weighting outliers and by preventing one interval from dominating the entire arc. Teams also run jackknife tests, hold out subsets of the data, refit, and see whether the preferred model structure changes. If the push term only helps when a particular site's frames are included, caution is warranted. In the early refits, the push improved the immediate post-encounter arc under several reasonable weighting schemes and subsets, but analysts were explicit that this conclusion must be revisited as new nights extend the timeline. Assuming the push is real for the moment, the next question is cause. 3 physical mechanisms cover most of the plausible space. The first is a short-lived directed jet. A small patch on the surface briefly vents gas and dust, either because a thin crust fails, a volatile pocket is exposed, or a rotating facet brings an active region into favourable sunlight. The gas flow acts like a tiny thruster. The dust boosts brightness for a few seconds to tens of seconds, and then fades as the flow shuts down or rotates out of view. The improvement in the fit is localised in time, and there is no need to invoke more than ordinary comet-like activity. This model becomes stronger if follow-up spectra, even days later, detect gas species that would be expected after such venting, or if repeated photometry shows low-level variability consistent with rotation gating of small active areas. The second mechanism is microfragmentation. A thin flake of surface material or a compact cluster of grains detaches. The shedding event increases the scattering area, producing a brightness step, and changes momentum slightly if mass loss is directional. In some comets, microfragmentation leaves a footprint in the inner haze, faint fans, subtle shelf-like features, or a longer than usual relaxation back to baseline brightness. Analysts therefore compare the radial profile of the inner haze before, during, and after the transient. In the encounter data, profiles did not show a strong persistent change, but the cadence and depth were tuned for timing, not morphology, so small features could have been missed. This model remains viable if later imaging reveals a residual asymmetry, or if the baseline brightness stays a notch higher than before. The third mechanism folds in the local environment. Near Mars, charged dust can behave differently, as it moves through the planet's patchy magnetic fields and variable plasma. A short change in charging conditions could redirect a dust fan or alter how grains are accelerated, producing a brief brightness spike and a momentary force if mass flow is redirected off-axis. This explanation is sensitive to timing and conditions. It gains plausibility if independent space weather measurements near Mars show a coincident shift in solar wind parameters or in the position of the bow shock. Without corroborating environment data, the environmental model is harder to prefer over a self-generated jet. Several lines of evidence test whether a course correction is more than a coincidence of geometry and cadence. One is continuity. If the push is real, a solution that includes it should continue to outperform a purely gravitational model for the immediate post-encounter segment, even as additional nights extend the arc. If the apparent benefit fades as the timeline grows, that means early gains may have been an artifact of limited data density, and the push term is being used by the fit to soak up noise. A second is consistency across independent pipelines. Groups using different centroiding algorithms, star catalogues, and distortion models should converge on similar residual patterns. If the pattern depends on a particular combination of software and settings, skepticism is warranted. A third is cross-band stability. Positions measured in different filters, taken nearly simultaneously, should agree within expected chromatic effects. A mismatch between, for example, red and green centroids would hint that the inner haze behaved differently by wavelength, and could have tugged the centroid without a real change in motion. Rotation-aware tests add another layer. If the transient is linked to a particular surface facet, repeating geometry at the same rotational phase may produce smaller echoes. Observers therefore flag predicted windows where the same face should reappear under similar illumination. A single affirmative repeat would not prove a push by itself, but a pattern of small, similarly timed brightenings with no corresponding path change would shift weight toward purely geometric or optical explanations. Conversely, another small improvement in the fit tied to a similar transient would push the analysis toward a physical impulse model with rotational gating. It is also important to quantify how small a course correction we're talking about. The implied change is at the millimeters per second level, far below anything that would matter for hazard or for long-term trajectory planning. That scale is exactly the regime where model choices, centroid methods, and station systematics matter. For that reason, orbit analysts often run families of solutions. One family uses only gravity. Another adds a standard set of small, continuous, non-gravitational terms to account for steady outgassing. A third allows a time-localized impulse. If the third family wins in the short segment after closest approach, and the first two remain adequate before and long after, that mixed picture favours a compact event near Mars rather than a change in overall activity state. A separate thread of discussion inevitably asks whether an impulse could be guided, that is, artificial. The threshold for treating that as anything other than speculation is high. Objective criteria would include a series of discrete thrust-like events that repeat at intervals unrelated to illumination or thermal cycles, pushes with directions that are not aligned with plausible venting axes and that maintain coherence across changing geometry, engineering-like regularity in timing or magnitude, and accompanying signals in bands where engineered systems might emit, none of which have been reported. In contrast, a single, time-localized push that coincides with a photometric flare leaves no radio signature and is consistent with venting physics sits squarely in the natural category. The data around Mars support the latter pattern. The cosmic coincidence side of the ledger also has concrete tests. Projection effects near a bright planet can exaggerate or suppress apparent motions. To control for this, analysts measure residuals at multiple distances from Mars and discard measurements made over backgrounds that are known to carry subtraction artifacts. They also compare the apparent improvement from a push term when Mars is in the field to improvement when Mars is out of the field. If the model only prefers an impulse when strong gradients and optical ghosts are present, that weakens the case for a true change in motion. In the encounter dataset, angle measurements of the tail and position residuals were computed both near and far from the strongest gradients. The preference for a brief push remained, though the team emphasised that later, cleaner geometry would provide a firmer answer. One subtle source of confusion is that an extra term can mask unmodelled noise as easily as it can capture real physics. For that reason, some teams split the encounter interval into several short windows and fit each independently. If a push is real, its preferred timing should land in the same narrow window across independent fits. If the timing wanders depending on which frames are included, the extra term may be compensating for small frame-to-frame centering differences. In the early analysis, the best timing clustered around the brightness spike, which is what you would expect if illumination changes and outgassing combine to produce a short pulse. It is also worth looking downstream toward what each interpretation implies for observation strategy. If a compact natural impulse is the right answer, the most valuable follow-up is continued dense astrometry to see whether any additional small pushes occur and to keep the ephemeris tight as 3i Atlas recedes. Simultaneous multi-band photometry during predicted rotational phases can test whether similar transients recur and whether their colour behaviour remains neutral, as expected for dust-dominated flashes. Deeper spectra shortly after any future spikes would probe for gas that might have been missed in the Mars window. If, instead, the improvement fades with added data and the purely gravitational model remains satisfactory, then the lesson is methodological. Prioritise core-weighted centroiding during brief activity, avoid aggressive background modelling near bright fields, and be cautious about interpreting small local fit gains during periods of rapidly changing geometry. One practical check that bridges both interpretations is to compare orbit solutions built from different subsets of stations. If the push is physical, a solution based on only a subset of observers should still show a similar improvement within noise. If the push is a quirk of one instrument's behaviour, the subset that excludes that instrument will not prefer it. Early subsets suggested the improvement was not confined to a single observer, strengthening the physical side slightly but still short of definitive proof. Finally, it helps to remember scale and context. Previous interstellar visitors taught the community to expect surprises in non-gravitational behaviour and light curve oddities. 3i Atlas adds a case where a brief localised change appears to have occurred during high-interest geometry. The conservative stance is to treat the course correction as provisionally real, natural and small, to continue testing that stance as the arc lengthens, and to design follow-up that can falsify it if it was an artifact of timing and processing. The alternate stance, that the fit improvement is a coincidence of cadence and geometry, remains viable until the preference for a brief push survives the next rounds of clean, well-separated measurements. Either way, the diagnostic path is the same. Keep measuring, keep methods conservative, and let the accumulated residuals decide whether 3i Atlas nudged itself, or whether our models blinked during the busiest minute of the campaign. Reports of brief radio fluctuations coincident with the optical flare prompted a basic question. Did 3i Atlas emit anything measurable in radio, or were observers seeing structure in noise shaped by equipment and the local spectrum environment? The first filter is definitional. A signal is a repeatable, statistically significant feature that appears in the same place in time-frequency space across independent systems with characteristics that match a sky source rather than local electronics or known transmitters. Pareidolia is pattern finding in stochastic data, compressions that create ringing, windowing that introduces spectral scallops, or algorithm choices that sculpt noise into ridges and chirps. Radio backends and processing steps are fertile ground for false positives. Waterfall plots are often rendered after decimation, resampling and windowing. Each step can introduce side lobes that look like narrowband lines. Automatic gain control can breathe during a bright continuum event elsewhere in the band, imprinting gentle waves that a matched filter might latch onto. Polyphase filter banks reduce leakage between channels but can generate comb-like artifacts if not tuned to the input sample rate exactly. If the system does on-the-fly radio frequency interference excision, the mask itself can create rectangular gaps that make surviving features look more structured than they are. The terrestrial spectrum is crowded. Aircraft transponders, satellite downlinks, cell towers reflecting off aircraft, and even digital camera electronics in the control room can show up if shielding isn't perfect. Near planetary encounters, additional emitters are in play. Deep space downlinks, radar campaigns, and relay passes. A narrowband line that sits perfectly at a known communications frequency shows no sky position dependence and vanishes when a notch filter is applied is not astrophysical. By contrast, a celestial signal typically drifts in frequency at a rate consistent with changing line-of-sight velocity as Earth rotates and the source moves. It strengthens when the telescope is on target, weakens or disappears when pointed away, and repeats in polarized channels according to a physical model, not the quirks of a single receiver chain. A disciplined triage playbook starts with simultaneity. Check whether two geographically separated observatories recorded the same feature within the same seconds and at the same sky coordinates. If not, the burden of proof increases dramatically. Next, test for pointing dependence. Run a quick on-off on cadence, stepping a degree or two off target to measure the local RFI field. If the feature persists off-source with similar strength, it is not coming from 3i Atlas. Examine drift behavior. A terrestrial carrier has either zero drift or a drift pattern tied to local multipath. An astrophysical narrowband will follow a smooth trend that you can predict from the known motions without contorting parameters. Inspect polarization. Many man-made transmissions are strongly polarized. A true celestial line can show polarization behavior, but it will match sky rotation and instrument model, not swap-handedness when a cable is wiggled. Multiple beam receivers provide an immediate cross-check. If a feature hits every beam equally, it is likely entering through a side lobe or the near field rather than from the target direction. If it is strongest in the on-target beam and falls off in the outer beams according to the known beam pattern, its origin is more likely to be celestial. Beamforming arrays add another test. Steer nulls across the suspected direction. If a null kills the feature at an angle inconsistent with the target's position, that's a strike against a sky source. Processing choices must be frozen during investigation. Lock the gain, disable adaptive RFI excision, and record raw complex voltage streams for short segments so that independent teams can rerun the detection with different software stacks. Export the exact time and frequency calibration information, clock source, local oscillator plan, bandpass shape, so downstream checks can exclude miscalibration. Share background monitors, local spectrum analyzer snapshots, known transmitter schedules, and any housekeeping logs that note retunes, LO unlocks, or temperature excursions in front-end electronics. The look elsewhere effect is especially pernicious when the community is primed by an optical event. If dozens of observers comb hours of data across gigahertz of bandwidth, the chance of finding an apparently coincident blip by random alignment is non-trivial. Pre-registering a narrow time window, a small frequency region, for example, bands known to be relatively quiet, and a minimal set of statistics reduces this trap. If a feature appears, the first questions are, does it recur in immediately adjacent windows? Does it survive modest rabbining and alternate window functions? And does it appear in the same way when the telescope is pointed at a blank sky position at similar elevation? False structure generators have recognizable fingerprints. Spectral combs at regular intervals point to digital electronics or poorly suppressed local oscillators. Chirps that begin at sub-integration boundaries hint at software buffer flushing. Vertical teeth that align to channel edges betray filter bank artifacts. Slanted streaks that change slope when the plot aspect ratio changes are graphic scaling illusions. Short-lived dots at harmonics of a bass frequency, repeating exactly across sessions, indicate intermodulation. None of these behaviours match a physical mechanism tied to an interstellar object near Mars. If a candidate survives these gauntlets, additional sanity checks tie it back to the broader context. Was any deep space transmitter operating at or near the candidate frequency during the window? Were ground antennas slewing or reconfiguring polarization? Did atmospheric conditions at the site change rapidly, producing phase decorrelation that a correlator tried to heal into a line? And crucially, does any plausible emission mechanism for 3i Atlas predict power at the candidate frequency with the observed bandwidth and timescale? For dust and gas-driven activity, coherent narrowband emission is not expected. Any radio counterpart would be broadband continuum or line emission from known molecules, neither of which aligns with the narrow-structured blips that circulate fastest online. A conservative, voiceover-suitable bottom line for this segment is simple. Weak, short radio features that vaguely line up with the optical flare are most likely artifacts of processing and the spectrum environment unless they pass multi-site, on-off, drift-consistent, polarization-consistent tests with raw data reproducibility. The burden of proof is high by design, and that standard protects analysts from reading patterns into static. The historical record of interstellar visitors frames how to proceed now. The first recognized visitor displayed a set of surprises: a large brightness modulation suggesting an extreme shape or a flattened, tumbling body, a lack of obvious coma in deep imaging, and a persistent small non-gravitational acceleration that did not square cleanly with typical water-driven outgassing at the observed distances. Competing explanations multiplied: exotic ices, a fractal dust sail, mechanical properties unlike familiar comets, because the window for observation was short and the data sparse. The key lesson was methodological rather than sensational. When phenomena sit near your instrument limits, cross-calibration and open data are more valuable than clever new hypotheses. Re-reductions, improved thermal modelling, and late-stage constraints from additional facilities reigned in the wildest claims without eliminating the fundamental oddity. A natural object with unusual physical behaviour is still the best fit to the full set of facts. The second visitor looked, in many respects, like a textbook comet. It carried a visible coma and tail, exhibited familiar gas bands in spectra, and behaved in ways that could be modelled with established dust and gas dynamics. It was also caught earlier and observed longer because surveys knew what to look for and because the community shifted into coordinated mode faster. The operational lesson was clear: quick, deep, multi-band coverage, especially spectroscopy, prevents overinterpretation by anchoring models in basic composition and activity data. With those anchors, even unusual details become constraints rather than invitations to speculation. 3i Atlas inherits both legacies and adds its own twist. The timing of a short optical flare near a planetary flyby, plus a small, time-localized improvement in trajectory, fits when a brief push is allowed, is a new combination in the interstellar sample. That novelty increases interest, but it does not demand new physics. The working space includes small, directed mass loss events, microfragmentation, and geometry effects that are easy to miss without high cadence. The deviations seen in tail orientation and the marginal, processing-sensitive ripple near Phobos are better treated as separate Mars environment questions than as properties of the interstellar object itself. What should be done differently now, given how the first two cases played out? First, commit to simultaneous observations over sequential ones whenever possible. Simultaneous dual-band photometry, simultaneous imaging and low-resolution spectroscopy, and parallel radio and optical captures reduce crosstalk between variability and filter changes. Second, standardize reduction recipes up front. Agree on aperture sizes, background models, centroiding algorithms, and error reporting before the next flare-like window opens, so that cross-team comparisons are apples to apples. Third, publish raw and minimally processed data rapidly to trusted repositories with sufficient metadata, clock provenance, detector linearity tests, star lists, and weather logs, to enable independent rederivations. Fourth, predefine statistical tests to avoid the look elsewhere effect. Specify which intervals, which frequencies, and which significance thresholds count as hits. Fifth, track and share environment monitors, solar wind conditions, bow-shock models, deep space transmitter schedules, and local RFI surveys. There's also value in explicitly ranking hypotheses by simplicity and testability. A compact jet fits both the optical and dynamical hints and predicts several follow-ups. Weak gas signatures near known bands if sensitivity is sufficient, low-level modulation tied to rotation, and no need for unusual materials. Microfragmentation predicts subtle, persistent changes in the inner haze profile, and possibly a slight sustained increase in baseline brightness. A glint predicts repetition at the same rotational phase under similar phase angle, but does not explain a push. Environment-driven dust redirection predicts correlation with space weather changes near Mars and wavelength or polarization, dependencies characteristic of charged grain dynamics. Each of these can be advanced or eliminated by specific scheduled measurements. None require leaping beyond comet physics. Comparisons to the first visitor's non-gravitational behavior have to be handled with care. That object's steady, small acceleration over weeks is not the same as a brief, localized push coincident with a flare. Lumping them together invites confusion. Equally, comparing 3i Atlas to the second visitor should emphasize compositional diagnostics. If spectra remain quiet while photometry remains active, the case for dust-dominated weak gas behavior grows, and gas-free explanations become less strained. Consistency across bands during future transients, no strong color change at the spike, would nudge the interpretation toward neutral dust or geometry rather than exotic volatiles. Communication discipline is part of the scientific method here. Avoid framing anomalies as proofs. State what was measured, where the uncertainties lie, and what would change minds. Lay out pre-registered tests. When preliminary conclusions shift after better calibration, explain why. The first visitor taught the cost of fast, flashy narratives. The second showed the payoff of methodical, multi-instrument coverage. 3i Atlas sits between those experiences. The best way to treat a short flare and a tiny course adjustment near Mars is to apply lessons already earned. Prioritize simultaneity, standardize methods, publish RAWs early, test rotation phase predictions promptly, and let consistent cross-checked residuals, not excitement, decide whether a few seconds near a planet rewrote a trajectory or just rewrote our interpretation of a busy minute in the data. The visible sign that a press event had been contemplated was a set of routine placeholders that typically precede high-interest briefings, tentative calendar blocks shared with partner institutions, draft run of show notes circulating among public affairs leads, and a short internal memo asking science teams for 2 slides each, one summarising the observing plan, one listing what not to claim. In the hours after the Mars pass, those placeholders disappeared from public-facing agendas, and the internal memo stopped short of a final call. Instead of a podium schedule and a list of speakers, communication staff shifted to holding statements and if-asked guidance. The wording changed from media availability following closest approach to the more cautious, updates will follow after data verification. That progression did not indicate that something dramatic was being hidden. It reflected a standard pivot from outreach mode to verification mode when an observation produces an unexpected feature, like the short, sharp brightening seen with 3i Atlas. Inside any large program, a press conference is a logistics and risk exercise as much as a science one. Before spokespersons walk into a room, several gates must clear. Technical owners must confirm that instrument health is nominal and that no sensitive operational details, telemetry rates, internal thresholds, or security-relevant configurations will be revealed inadvertently. Legal and policy teams review for export control issues when plots include high-resolution pointing or spacecraft performance margins. Partner agencies ask that their own review boards sign off on shared figures. If the event touches more than one mission or centre, a chairperson has to reconcile differences in phrasing so that one project does not imply something another project cannot endorse. All of this takes hours even when nothing is wrong. If a dataset is still being re-reduced in parallel by multiple groups, convening a press conference risks freezing the narrative too early. The first alternative to a full press event is a backgrounder, a short note to accredited reporters summarising what is known, what is under review, and what to expect next. Even that requires confidence in the time base, calibration, and cross-facility consistency. After the 3i Atlas flare, the science teams were still checking whether a brief non-gravitational push improved immediate post-encounter fits, and whether centroiding methods agreed in the frames bracketing the spike. A backgrounder that mentions a possible small impulse without those checks invites misquotes that harden into headlines. The safer move is to let the quick-look chatter circulate within the observing community while official channels stay narrowly descriptive. Closest approach occurred as expected. Data are being compared. Further details will be shared when the analysis is complete. There is also the practical matter of who would stand at the lectern. Each spokesperson must be able to answer questions that range from benign, what is a light curve, to surgical, why did the residuals shrink only, when you added a time-localized transverse term. If the person best suited to those questions is busy leading a tiger team on the reduction itself, you do not pull them off the work to prepare talking points and rehearse Q&A. The next best option is a communications-savvy scientist with direct knowledge, but that person will insist on final plots, not screenshots. Absent those, a room full of cameras introduces more risk than reward. The internal timeline after any surprise follows a well-worn sequence. Collect all raw files and calibration frames, run at least 2 independent reduction pipelines, compare results on a shared dashboard, and draft a one-page disposition that states what the feature is, what it is not, and what could change the assessment. Only when the disposition reaches a stable state does public affairs schedule a briefing. In the 3i Atlas case, that one-pager was still labelled interim, as long as the astrometry subsets were being jackknifed, and the photometry was being re-reduced with alternate aperture strategies. Under those conditions, the decision not to hold a same-day press conference is not silence, it is adherence to process. Another factor is the press conference's scope. If the event would centre on a short-duration brightening with modest amplitude, accompanied by a small, time-localised improvement in trajectory fits, a written update can carry the message with less risk of overinterpretation. Press rooms tend to amplify speculation through follow-ups. Could this be artificial? Is this like that earlier interstellar object? Are you hiding anything? A measured blog post or bulletin can lay out the observations in plain terms without having to field questions that tempt overreach. Agencies have learned that an hour at a podium during an evolving analysis can create weeks of cleanup communications. Coordination with partners adds delay, even when everyone agrees on the facts. If a Mars orbiter's instrument data are part of the story, their project office may require internal review boards to sign off before a figure leaves the building, even if the figure shows only background stability. If a ground facility contributed key photometry, Its institutional press office may want assurance that release policies are respected and that credit lines are correct. If international collaborators have related observations under their own embargoes, simple courtesy requires aligning language so no one's process is compromised. Each of these steps is routine. Together they push a potential press conference past the first news cycle. There is also a defensive reason to cancel a planned briefing, protecting the integrity of downstream proposals and telescope time. If a room full of reporters hears we saw a flare at this time, the next question will be, what next? The honest answer, we need simultaneous multi-band photometry, deeper spectra, and continued astrometry. Sounds like a shopping list. Proposal competitions are sensitive to the appearance of inside advantage. Announcing preliminary interpretations from a lectern can be construed as staking claim on follow-up resources. Many teams prefer to publish a neutral status note and share technical guidance privately with observers who have already been contributing, thereby avoiding the optics of lobbying through the press. Against that backdrop, the press conference that did not happen around 3i Atlas is best understood as an ordinary byproduct of verification. Drafts existed, speakers were considered, then calibration and cross-checks took priority. Public statements narrowed to facts, and the podium stayed empty. When the internal disposition hardened, short, real brightening, small provisional fit improvement with a time-localized push, no operational anomalies. The communications plan shifted toward written updates and targeted technical notes rather than a live event. The broader question of why agencies go dark has an answer that is procedural rather than mysterious. The first category is verification. When an anomaly might be instrumental or environmental, the playbook says to run independent pipelines, freeze processing parameters, and reproduce the feature before speaking. That takes time. The second category is operational safety. If there is any chance that a message will pressure a flight team to keep an instrument in a risky configuration to get a better public image, communications wait until the vehicle is fully back in standard modes. The third is partner coordination. Multi-agency activities require shared language and agreed-upon figures. Each partner has its own review cadence. There are also policy reasons to pause. Export control regimes and internal security policies can require redaction of plot axes, timestamps, or configuration data. When a figure must be altered to meet those rules, legal and technical leads confer to ensure the scientific meaning survives. That adds days. In parallel, privacy and attribution policies need attention. If community observers supplied crucial light curves, agencies avoid republishing those plots without consent. Negotiating credit lines, logos and captions is not glamorous, but it is part of responsible communication. A fourth driver is uncertainty management. Early numbers often carry large error bars, and internal drafts show a range of values that converge as reductions stabilize. Releasing a preliminary value and revising it later is normal in science, but damaging in public if the revision is framed as a walkback. The communications playbook therefore favours qualitative descriptions, short-duration brightening, small improvement in fit immediately after the event, until several nights of additional data shrink the uncertainties. This choice reads as silence to audiences hungry for numbers, but it preserves credibility. A fifth element is workload. The same people who would draft talking points and rehearse answers are usually the ones running the calibrations and coordinating with external teams. During the most intense hours, a communications freeze protects limited human bandwidth. The pause is not a communication strategy so much as a triage decision. Fix the analysis first, then talk. Legal and reputational risk also appear on the checklist. If an event might be misinterpreted as evidence for an extraordinary claim, agencies craft language that anticipates and neutralizes common misreadings. Phrases like consistent with and provisionally favours are used intentionally to avoid prematurely naming causes. That requires review by subject matter experts and by communication staff trained to spot ambiguous phrasing. When a draft cannot be made both accurate and unambiguous quickly, the safer option is to delay. A sixth driver is alignment with scientific norms. If a team expects to submit a short technical note or circular to the professional community, the agency may choose to let that appear first or in parallel. Press material then points to the technical summary without getting ahead of it. This sequence reassures researchers that public messaging is anchored to citable analysis, not to social media momentum. There are finally structural reasons why external observers perceive silence, even when internal work is brisk. Public dashboards show only a subset of telemetry and schedules. A switch from high-rate playback to two-way navigation support looks like a lull, even though the ground segment is busy and the spacecraft is healthy. A momentum dump, star tracker recalibration, or routine instrument maintenance can be scheduled exactly when geometry is best, producing an unfortunate but harmless overlap with high public interest. Communications staff often avoid narrating these benign events in real time, so that the public does not conflate them with anomalies. That restraint is a choice to keep the record clear, not an attempt to hide operations. When agencies do speak during verification, wording is deliberately spare. You see formulations such as, teams are reviewing data from multiple instruments, routine checks are underway, and we will share details once cross-validation is complete. These phrases are not stock evasions. They are placeholders that buy time for the exact steps you would want them to take. Confirm clocks, rederive centroids with alternate methods, compare residuals across stations, and test model sensitivity to aperture and background choices. In the 3i Atlas window, that is exactly what was happening. There is a risk that prolonged quiet invites speculation to fill the gap. The mitigation is to publish process, not conclusions. Brief notes that list what is being checked. Timing integrity, detector linearity, centroid bias, station-to-station consistency help audiences understand that silence is work, not absence. When results do arrive, they land on ground the public has watched being prepared. Across programs, the Go Dark playbook is not a single switch but a ladder. First rung, slow social updates and route media to a holding statement. Second, restrict new figures to those cleared by technical leads, even on internal channels. Third, convene cross-center review for any claim that could require operational changes. Fourth, align with partners and legal on language. Fifth, return to normal cadence when either the feature is reproduced and bounded, or it is shown to be an artifact. In the case of 3i Atlas, the ladder was climbed just high enough to protect analysis during the busiest hours, then climbed back down once the immediate checks were complete. For creators and observers trying to read institution behavior, the heuristics are simple. If routine status pages stop posting new numbers, but later deliver a single, carefully worded summary, assume verification. If instrument teams keep publishing unrelated, scheduled content while avoiding fresh plots from the event window, assume internal reviews are ongoing. If partner institutions mirror the same posture, assume coordination rather than suppression. And if, after a reasonable interval, the language tightens around a small set of agreed facts, short optical brightening across independent facilities, no instrument faults, modest local improvement in fit with a brief non-gravitational term, assume the process worked as designed. Private operators and philanthropically backed facilities stepped into the gap with speed and a different set of incentives than government missions. Robotic telescope networks offered immediate schedule swaps to point at 3i Atlas, delivering rapid astrometry and high-cadence light curves with consistent hardware and calibrated pipelines. Several commercial survey cameras pushed out engineering cuts of their nightly stacks. Lower dynamic range than science-grade releases, but invaluable for time stamping the onset of the brightening. Citizen science platforms coordinated small scopes to run standardized apertures and synchronized timing, yielding dense, distributed coverage that professional time allocation systems cannot match on short notice. University radars discussed feasibility notes, but largely sat out. At Martian distances and beyond, even powerful transmitters struggle for enough return signal, and bistatic experiments require long planning horizons and clean geometry. The more realistic private radio contribution came from spectrum monitoring. A few independent stations recorded raw voltage dumps across bands most likely to be quiet, not to hear 3i Atlas directly, but to rule out local emitters masquerading as sky signals during the window. Data ownership and release policies became a practical friction point. Commercial providers who sell calibrated photometry were willing to release thumbnail products or summary plots quickly, but held full-resolution frames under license until routine review cleared them. That created two tiers of analysis: public reconstructions based on compressed imagery, and private re-reductions inside institutions with data-sharing agreements. To reduce confusion, several providers published minimal method-focused notes, time base, filters, and reduction choices, so others could replicate the shape of their results without copying the data outright. Where non-disclosure agreements applied, teams at least confirmed timing and qualitative behaviour via neutral language, which helped stabilise the community narrative without breaching contracts. Social amplification added noise and reach in equal measure. A high-profile technology founder posted a dramatic brightness plot with aggressive smoothing and no-axis labels, prompting millions of impressions and immediate claims that the flare implied guidance. Observers with calibration authority responded by reposting unsmoothed, time-stamped curves and stating what the graph could and could not prove. A short optical increase, yes. Evidence for anything engineered, no. The episode underlined a standing lesson for fast-moving events. Plots leave the lab the moment they appear on a screen, so internal quicklook tools should carry time bases, units, and provenance in frame to survive cropping and reshares. Private network strengths, speed, automation, geographic reach came with constraints that professionals accounted for in downstream fits. Absolute photometric 0 points from some systems drift with temperature and focus, so the community treated their light curves as differential during the critical minutes and anchored amplitudes later against calibrated standards. Astrometry from ultra-wide cameras can suffer from field distortion. Orbit fitters weighted those points conservatively and required cross-confirmation from narrower fields before accepting any small post-event trajectory improvement. These practical guardrails let private data shape the immediate story without outsizing their formal impact on the long-arc solution. Industry telemetry contributed context in less obvious ways. Satellite operators with precision star trackers reviewed whether their sensors recorded anomalous glints or background fluctuations along sightlines that passed near Mars during the window. None reported anything inconsistent with ordinary stray light, which helped reject a handful of viral videos claiming long flashes across the disk. Insurers and conjunction analysts check their catalogues for any debris or unmodelled objects that could plausibly explain a coincident flash. The checks were negative, a quiet data point that reduced one more speculative branch. Philanthropically backed large aperture facilities, some operated through private consortia, offered deep imaging and low-resolution spectra on short notice via discretionary time. Their value was not speed alone, but stability. Well-characterized instruments, repeatable flats and biases, and staff who could share pipeline details so that independent teams could rerun reductions from raw frames. Even a non-detection of gas at useful sensitivity, when accompanied by clear limits and instrument response curves, helped narrow the space of viable explanations for the flare. In several cases, directors approved service mode mini-programs to track the tail's angle and inner haze structure as the object receded, filling in the slower methodical measurements that smaller telescopes cannot deliver once the target fades. The public-private interface worked best where expectations were set early. Community coordinators circulated a short, neutral checklist for contributors, UTC stamps, fixed apertures during suspected transient windows, simultaneous dual-band where possible, and both core-weighted and aperture-weighted centroids, so that data arriving from backyard rigs, institutional telescopes and subscription networks could be merged without guesswork. Private providers that follow the checklist found their products adopted quickly into combined plots and residual analyses. Those that did not were still useful, but only qualitatively until re-reduced under common assumptions. The net effect of industry participation was to compress the time between an ambiguous moment and a testable picture. Private networks brought cadence and coverage. Philanthropic facilities brought depth and calibration. Social platforms forced clarity about methods. None of these replaced the need for government missions or archival rigour, but they changed the tempo. Instead of waiting for a single, official plot days later, analysts compared half a dozen independent measurements within hours, rejecting artifacts and documenting a short optical event that coincided with a small, time-localized improvement in post and counterfeits when a brief push was allowed. The division of labour was clear. Private actors carried the first wave. Institutional teams consolidated and hardened the result. The trajectory work that followed the Mars pass led naturally to outer system planning, even under conservative assumptions. A short, localized impulse near closest approach shifts a hyperbolic path by a small but non-negligible amount, which propagates into weeks to months changes in where and when 3i Atlas crosses key heliocentric distances. Orbit analysts produce side-by-side families of predictions, one purely gravitational, one with continuous low-level activity, and one that included a brief post-Mars push before returning to gravitational motion. The differences were modest at first, arc seconds in the sky, minutes in timing, but they compound with distance. By the time the object heads toward the outer planets, the family choice determines whether certain observatories see it at favourable elongations and phase angles, or miss the optimal windows entirely. Planning for giant planet opportunities started with geometry rather than assumptions. Analysts mapped when the object would reach the orbital distances of Jupiter and Saturn, and whether it would pass anywhere near their spheres of influence. Near here means close enough to alter observing plans, not close enough to alter the object's path in any dramatic way. Even a distant, many millions of kilometers crossing can be scientifically useful if it yields configurations where sunlight, the object, and an observer align to maximize forward scattering or thermal emission sensitivity. On those dates, large mirrors and sensitive infrared instruments become valuable because reflected light brightness fades quickly as distance increases, while thermal contrast can, in some cases, remain detectable if activity continues at a low level. Coordination with assets already in the outer system was considered carefully. A spacecraft at Jupiter carries instruments optimized for auroras, atmospheres and magnetospheres, not for pinpointing a faint interstellar visitor in deep space. Wide-angle cameras or star trackers could, in principle, provide position constraints or detect a brightness bump under perfect conditions, but neither pointing authority nor telemetry budgets are trivial to repurpose. The more realistic contribution from in situ missions is environmental context. Plasma and field measurements that bracket any dust or ion tail behaviour if the object crosses solar wind regimes with unusual structure near the planet's orbits. From Earth, the next year of observations was divided into practical blocks, immediate post-Mars consolidation to shrink ephemeris uncertainty, an intermediate phase focused on rotation, low-level activity searches, and tail morphology stability, and an outer planet distance phase where only the largest facilities would keep signal above noise with meaningful cadence. Within each block, observability was set by solar elongation limits. Space-based infrared observatories have strict sun angle constraints. Ground-based telescopes are limited by twilight and season. Schedulers translated the trajectory families into concrete go-no-go calendars, so time allocation committees could decide early whether to allocate deep exposures in the months when a detection still carries compositional or dynamical information. Instrument modes were chosen to match realistic signal expectations. Optical images stayed with broad bands for maximum throughput and cadence during transient windows, adding narrow band only if prior spectra justified the cost. Low-resolution spectra, taken opportunistically when the object is highest and the sky driest, prioritize continuum shape and the strongest volatile bands. Any detection would be surprising but decisive. Thermal infrared, while photon-starved, offered one of the few routes to constrain particle sizes and activity if the reflected light signal drops too low. It also provides independent checks on albedo assumptions used to convert brightness to size. Radar was effectively off the table beyond the inner system given signal budgets. As the path diverged slowly between the family models, each new astrometric night pulled the predictions together or pushed them apart. If the solution that included a brief push kept outperforming the purely gravitational model for the immediate post-Mars segment, without creating tension later, planners gave more weight to its dates for outer system windows. If the difference evaporated with longer arcs, teams reverted to the simpler model and used the exercise to refine requirements. More emphasis on core-weighted centroids near complex backgrounds, less on aggressive background subtraction that can bias positions when the coma changes. Uncertainty management shaped how outer planet opportunities were presented to observatories. Schedulers dislike maybe targets. They want quantified probability of success and clear, falsifiable triggers. Orbit teams therefore packaged windows with explicit criteria. Proceed if uncertainty ellipses shrink below a specified size by a certain date. Skip if weather scrubs the pre-window nights, or if activity metrics fall below threshold. That framing allowed Q schedulers to treat 3i Atlas as a high-value, time-sensitive target, rather than as an open-ended commitment. The scientific goals at outer distances were modest and tightly linked to earlier anomalies. First, test whether any short-lived optical events repeat at predicted rotational phases when geometry is favourable, which would strengthen rotation-gated jet interpretations for the Mars flare. Second, measure tail direction and curvature under quieter solar wind conditions far from Mars to see if the didn't behave segment was a local effect. Third, accumulate enough deep photometry to refine the absolute brightness, and by extension, size albedo ranges as the phase angle changes. Fourth, attempt thermal detections at the deepest facilities to bound dust production at large distances if any persists. Partnerships were formalised to prevent the outer system campaign from fracturing into one-off efforts. A central ephemeris server, updated nightly, published the best fit solution with clear provenance and a changelog. A small working group maintained standardised reduction recipes and a shared repository for raw frames and calibration files, so that deep integrations from different mirrors would be co-reduced under identical assumptions. Citizen science networks retained a role by covering predicted phase windows at high cadence, even if their sensitivity would no longer resolve persistent tails. A single, time-stamped photometric bump would still be valuable. Because the object will fade steeply as it recedes, expectations were set early around what success looks like beyond Mars. A handful of deep, clear detections at key geometries can answer more than dozens of shallow, scattered ones. Negative results, reported with honest limits, are as useful as detections in deciding which physical explanations for the Mars-time anomalies survive. And if the path threads a geometry near a giant planet that allows even an indirect environmental test, field orientation, dust charging conditions, or forward scattering boost, those nights will be the most informative of the late campaign. Whether or not 3i Atlas passes anywhere newsworthy relative to the outer planets, the framework built after Mars, trajectory families, pre-registered tests, standardized methods, and clear go-no-go criteria ensures the remaining observing time is spent where it advances specific questions. The object's path is unbound and its brightness budget is unforgiving, but the method is scalable. Minimal assumptions, fast ephemeris feedback, and measurements tuned to discriminate among a small set of natural mechanisms for a short-lived event that briefly complicated an otherwise straightforward escape through the solar system. The competing explanations fall into three broad classes: a natural event consistent with known comet-like behaviour, a natural event driven by less familiar but still plausible material properties or environmental effects, and an engineered cause. Each class makes different testable predictions about photometry, spectra, morphology, and dynamics, and the value of the existing data is in how well it constrains those predictions rather than in declaring a winner outright. The natural comet-like interpretation treats the flare as a short, directed mass loss episode, and the small fit improvement after the pass as the recoil you would expect from that episode. Mechanisms include event opening when a thin crust fails, a rotationally gated jet turning into and out of favourable sunlight, or microfragmentation that briefly increases scattering area and alters momentum. In this view, the step-like light curve, the lack of strong colour change across common bands, and the time-localised preference for a small push are all internally consistent. It does not require continuous non-gravitational acceleration. It requires only a compact impulse coincident with a short brightness increase. This model predicts several follow-ups. First, low-level, rotation-linked variability should be detectable if the active area comes back into view under similar geometry. Second, spectra obtained soon after any future transients may show weak volatile features even if earlier attempts were inconclusive. Third, inner coma profiles should show subtle, temporary asymmetries near the nucleus during and immediately after a flare, relaxing as emission shuts down or rotates away. Fourth, tail direction should return to the simple anti-solar orientation on timescales of minutes to hours once small grains dominate the scattering again. Finally, long arc astrometry should converge so that only the immediate post-event segment benefits from a brief push. Away from that window, a gravity-only solution should remain adequate. A refinement within the same natural class as a composite event, a specular flash superimposed on a weak jet. A glint explains the sharp colour-neutral rise. A small, nearly coincident jet explains the tiny recoil. This combination predicts repetition of photometric spikes at specific rotational phases when the facet realigns, with little or no corresponding path change unless venting recurs at the same moment. In practice, that means future short events could appear without an accompanying fit improvement. If those spikes repeat with the predicted phasing and no dynamic signature, the composite model gains weight. If they do not repeat but a fresh time-localized fit improvement appears after another transient, a pure jet or microfragmentation becomes more likely. The natural but less familiar class keeps the cause in physics and chemistry and looks for differences in material inventory or environmental coupling that can mimic or amplify short events. One subset emphasizes supervolatile ices that activate far from the sun, thin mantles that fail abruptly, and phase changes in irradiated ice that release stored energy quickly. This path predicts early distance activity thresholds that do not match water-driven expectations, weak or unusual gas ratios in spectra, and dust dominated by relatively large neutral-coloured grains that flatten colour changes during a flare. Another subset focuses on electrostatic and plasma effects that reconfigure dust fans in planetary environments. Near Mars, variable charging and patchy fields can alter how grains lift and accelerate. A brief change in that environment can redirect mass flow long enough to create a sharp brightening and a small time-limited off-axis force. This line of reasoning predicts correlation with space weather monitors near Mars, mild wavelength or polarization dependencies characteristic of charged grain dynamics, and negligible signals once the object is far from the planet's bow shock. A third subset looks at mechanical properties: fragile, low-cohesion aggregates that shed flakes cleanly, smooth, compacted facets that produce strong glints without large mass loss, or a rotation state that gates sunlight onto small active patches on short timescales. These scenarios predict frequent small amplitude brightness structure tied to rotation, but few sustained changes in the overall activity budget. Within that second class, a critical divider is persistence. If the post-encounter trajectory continues to favour a small, time-localised push only in the immediate segment, and future tracking shows no need for ongoing non-gravitational terms, the case for an exotic continuous driver weakens. Conversely, if small, repeated improvements appear at predictable rotational phases or under specific phase angles without corresponding gas detections, arguments shift toward unusual surface textures, electrostatics, or a volatile mix not often seen in solar system comets. Measurements that help decide among these include simultaneous dual-band photometry during transient windows to look for subtle colour changes, simple two-angle polarimetry to probe grain properties, deeper spectra shortly after any future flare, and continued high-precision astrometry to test whether the push remains confined to narrow windows. The engineered interpretation requires a higher standard of evidence than the other two because its priors are extremely low and because ordinary mechanisms already reproduce key features. To be credible, it needs signatures that are difficult to fake with natural processes and easy to verify independently. Examples include narrow-band radio carriers with Doppler drifts that match sky motion, persistent across sites and polarizations, repeated discrete impulses with timing and direction that do not follow illumination or thermal cycles, glints or light curve modulations on a cadence that implies controlled orientation rather than rotation, thermal emission that remains inconsistent with solar heating under all reasonable assumptions, or the appearance of multiple co-moving fragments maintaining fixed geometry in ways that dust physics cannot sustain. The present dataset does not show those signatures. The radio fluctuations reported near the flare are weak and inconsistent across systems. Photometric spikes are singular and modest. The small fit improvement is confined to a narrow window and is consistent with a short mass loss episode, and there is no evidence of repeated thrust-like events or of orientation control. A disciplined way to treat the engineered hypothesis is to lay out change my mind criteria that, if met, would elevate its probability. These include detection of a stable, narrow-band transmitter that appears only when pointed at 3i Atlas and exhibits the correct Doppler behaviour over multiple nights. 2 or more discrete on-off impulses separated by time intervals that remain constant in inertial space rather than in the object's solar geometry. A light curve modulation that damps tumbling and converges toward a preferred attitude independent of solar torque. Or a high-contrast, non-natural spectral feature in reflected light that persists across phase angles. Absent such evidence, the engineered interpretation remains a low-weight tail in the distribution. Bias control matters across all three classes. The optical flare sits close to instrumental limits, so confirmation bias is a risk. Once a screenshot circulates, observers may see structure where none exists. That is why simultaneous independent reproductions with locked processing parameters carry more weight than single, aggressively processed plots. The same is true for dynamics. A brief improvement in fit can be soaked up by an extra term even when small centroid biases or background gradients are the real cause. Jackknife tests, station-by-station comparisons, and core-weighted centroids are the antidotes. Any interpretation that rises or falls on a single facility, a single method, or a single night should be treated as provisional. A practical decision frame for weighting the three classes uses only the strongest constraints to date. First, the brightness increase is short, high contrast, and colour neutral within uncertainties. It appears across multiple instruments with consistent timing. Second, spectra near the event are low signal to noise and do not yet show decisive gas signatures. Limits are informative but not final. Third, Astrometry just after the flare prefers a small time-localized push. This preference weakens or strengthens as the arc lengthens, and that evolution remains the key discriminator for dynamics. Fourth, tail morphology largely returns to nominal anti-solar orientation after the window. Deviations around Mars can be explained by transient geometry, grain size mix or local environment. These constraints jointly support the simplest natural models first, keep room for less familiar natural effects if specific correlations appear, and place the engineered option at the threshold that demands extraordinary, cross-validated evidence. Each class also carries clear near-term tests. For the comet-like jet or microfragmentation case, monitor predicted rotational phases for repeat spikes, pursue deeper, early-time spectra after any future event, and keep astrometry dense enough to see whether small impulses recur. For the unusual but natural class, correlate any transient tail kinks with space weather monitors at Mars-like heliocentric distances. Attempt simple polarimetry to detect grain property changes, and look for activity turning on or off at distances that favour super-volatile interpretation. For the engineered class, run coordinated multi-site radio campaigns with raw voltage capture over quiet bands during future transient windows. Pre-register time intervals and detection thresholds to curb the look elsewhere effect, and scrutinise any claims of repeated thrust-like impulses for independence from illumination and thermal cycles. When the same measurements serve multiple hypotheses, priority should go to those. Simultaneous dual-band imaging during a transient test dust colour and reduces timing ambiguity. Core-weighted versus aperture-weighted centroid agreement checks photocenter bias while feeding orbit fits. And rapid, low-resolution spectroscopy near the event window can catch fleeting gas even when deep spectra later fail. Those are efficient because they either confirm a natural compact mass loss episode, push the discussion toward less familiar but still natural mechanisms, or show a pattern so deliberate and repeatable that a non-natural explanation would have to be entertained seriously. The working allocation of weight based on parsimony and current constraints is straightforward. A brief natural event, jet, microfragmentation, or a glint plus jet composite, accounts for the light curve and the localized dynamic preference with the fewest assumptions. Less familiar but natural mechanisms remain available if forthcoming measurements tie transients to space weather or to material properties that differ from common solar system comets. The engineered interpretation sits at the floor, not because it is logically impossible, but because it lacks the specific, repeatable signatures that would force a re-ranking. The path forward is not to argue priors, but to collect the measurements that differentially support or eliminate each class. Repeated phase-locked spikes, early time spectra, polarization during kinks, and continued unbiased astrometry that either confines the push to the Mars window or shows that 3i Atlas produces small discrete impulses, again under conditions that natural models cannot easily reproduce. A coherent plan for what to do next starts with a single objective: convert a short, ambiguous interval into a set of measurements that discriminate cleanly among the few remaining explanations. That requires a test matrix, scheduled windows, and shared methods. The matrix maps each hypothesis, compact jet, microfragmentation, glint plus weak jet, environment-driven dust redirection, to specific signatures that can be confirmed or falsified with realistic instruments. The windows are anchored to rotational phase predictions, favourable phase angles, and the object's visibility constraints. The methods remove avoidable ambiguity by fixing aperture strategies, centroiding, time bases, and calibration routines across teams. For photometry, the default posture is simultaneous imaging in two bands rather than cycling filters. Dual band pairs remove timing offsets that otherwise blur short changes, and allow simple colour indices to be computed frame by frame through any future transient. Apertures remain fixed in pixel space during predicted windows, with growth curve checks applied after the fact to confirm that the measured amplitude does not hinge on aperture choice. Comparison stars are pulled from a small local ensemble with colours that bracket the neutral tone already seen. 0 points are anchored once per run, while transient analysis uses differential light curves to avoid drift. Every sequence logs per frame seeing and background summaries, so that later reductions can test sensitivity to point spread function changes. Astrometry needs density rather than depth during short windows and depth rather than density outside them. Near predicted phase peaks, exposures are kept short enough to avoid trailing, and centroids are reported in two forms: core-weighted fits that suppress coma and larger aperture centres of light that capture any motion of the inner haze. Positions are tied to consistent star catalogues and plate-scale solutions documented alongside the frames. Immediately after each window, teams run jackknife fits, dropping one station at a time, and report whether the preference for any brief push persists without a single facility's input. Outside transient windows, longer integrations tighten the ephemeris and reduce covariance growth, ensuring that future phase predictions remain accurate enough to schedule new tests. Spectroscopy is opportunistic but targeted. Low-resolution spectra taken as early as possible after any new spike prioritise continuum behaviour and the strongest volatile bands that would betray a real gas release. Even a non-detection is valuable if the sensitivity and time since the photometric feature are reported honestly. Upper limits constrain the mass loss budget implied by any dynamic preference for a brief impulse. When dual-arm or dual-camera systems are available, simultaneous spectral and imaging captures prevent misalignment between a fading flare and late spectrum. Polarimetry is an efficient discriminator when conditions allow. 2 angles are enough to flag grain property changes during a kink in tail orientation or a short brightness jump. Real dust near forward scattering geometry shows predictable polarization behavior. Optical ghosts and unsharp mask artifacts do not. Simple, short polarimetric snippets inserted into high cadence blocks yield more leverage than long standalone polarimetric runs taken hours later. Radio coverage remains conservative. Stations that can record raw voltages over quiet bands during predicted windows should do so with fixed gain, disabled adaptive excision, and locked time and frequency calibration. The goal is not to hear 3i Atlas in a narrowband sense, it is to make any claimed feature reproducible across sites, with the correct Doppler drift and pointing dependence. An agreed triage, on-off on pointing, multi-site simultaneity, drift consistency and polarization checks, keeps the bar high and the false positive rate low. Tail morphology work continues but with tighter controls. Teams avoid sharpening near Mars-like glare and instead apply gentle, large-scale background modelling with masks that grow with radius. Position angle rotation tests distinguish camera-fixed ghosts from sky-fixed features. When forward scattering geometry is favourable, schedulers allocate short windows for deep stacks that can test whether the post-Mars didn't behave segment was a local plasma or projection effect rather than a persistent property of the object. Isophotoanalysis within a few thousand kilometres of the photocentre, repeated at several epochs, is the quickest check for multi-jet behaviour or subtle inner haze asymmetries that would support a compact jet or microfragmentation episode. Simulations run in parallel to observations. Dust dynamics overlays, families of syndine/synchrone maps biased toward larger grains for minutes after a flare, are pre-generated for each predicted window so that measured tail angles can be compared in near real time. Simple thermophysical models, even with broad priors, provide start-stop expectations for when a thin crust might fail under changing illumination. Neither class of model is trusted on its own. Both are used to design discriminating observations and to avoid over-interpreting a single frame. Data governance is explicit. Raw frames, calibration sets, and minimal logs are deposited in a shared repository with clear provenance and versioning. Reduced products carry full parameter listings, aperture radii, annulus definitions, centroiding algorithms, catalogues and software versions. Time bases are UTC with mid-exposure stamps in headers and in human-readable logs. A small methods group curates a living reduction recipe, records deviations, and notes their impact on the final numbers. These procedural details matter more than any one night's plot. They are what convert a transient into a constraint. Scheduling is framed with go-no-go triggers. A window proceeds if the ephemeris uncertainty ellipse falls below a specified size by a set date, if weather forecasts at key longitudes cover at least one full rotation phase, and if at least one dual band and one polarimetric instrument can commit to the cadence. A window is skipped if those conditions fail, and rescheduled without ceremony. This discipline prevents resource drift toward marginal low-yield nights as the object fades. Community contributions remain central. Citizen science networks and subscription telescope arrays are assigned roles that play to their strengths. High-cadence dual-band photometry through predicted phase windows. Short, repeated astrometric bursts to bracket any new impulses, and long, steady light curves to refine the rotation state. Their products are treated as differential during the event and anchored to calibrated standards later. A short checklist, UTC stamps, fixed pixel space apertures, simultaneous bands where possible, paired centroid methods, and per-frame seeing metrics keeps heterogeneous data mergeable. Communications follow the verification playbook used earlier, but with process made visible. Public notes list what is being tested in each window, rotation phase repeatability, color neutrality during spikes, centroid agreement, tail angle under quiet solar wind conditions, and what would change the working interpretation. When preliminary numbers shift after re-reduction, a one-line cause is given, updated catalogue, corrected background model, or refined centroiding. This approach reduces the temptation to fill quiet periods with speculation and keeps focus on admissible tests rather than attention-grabbing claims. Decision criteria for re-ranking hypotheses are pre-registered. A compact jet remains the default if a repeat spike appears near the same rotational phase with neutral colour and no long arc need for new non-gravitational terms. Microfragmentation gains if inner haze profiles show small persistent asymmetries or if baseline brightness steps upward after a transient. A glint plus jet composite rises if photometric spikes repeat without any dynamic signature, while a rare spike aligns with a short fit improvement. Environment-driven redirection becomes more likely if a tail kink correlates with independent solar wind changes at similar heliocentric distances away from Mars. An engineered cause is considered only if narrowband radio signals with correct Doppler behavior appear across sites, or if discrete, thrust-like impulses recur with inertially fixed timing unrelated to illumination. Instrument safety and resource stewardship stay in view as the object recedes. Exposure times are kept within detector linear regimes. Mosaics avoid configurations known to produce internal reflections near bright planets, and downlink budgets are respected by scheduling deep stacks when the object is highest and conditions are stable. Large mirrors focus on a few well-chosen nights rather than many shallow attempts. Negative results, no spike at the predicted phase, no gas in early spectra, no polarimetric change during a kink, are reported with limits that downstream modelers can use. The outer system segment of the plan is moderate by design. A small number of deep integrations at favourable elongations test where the tail orientation has settled into a simple, anti-solar shape far from Mars, and whether any low-level activity persists. Thermal attempts at the largest facilities bound dust production under cold conditions. Observing time is justified as a final check on whether the post-Mars behaviour was a local effect or a general property of 3i Atlas. A final administrative thread closes the loop between operations and science. The ephemeris server posts nightly best-fit solutions with clear changelogs. A small working group signs off on any claim that a brief push remains preferred in the immediate post-event arc. and a standing note explains when that preference disappears as the timeline extends. That transparency prevents a single early fit from ossifying into narrative and makes it clear when a course correction was a localized feature rather than a persistent dynamical signature. A practical risk register is maintained alongside the plan, known failure modes, unsharp masking that creates ripples, background overfitting that carves rings, catalogue changes that shift plate scales, and DSN-driven schedule gaps that look like silence, are listed with mitigation steps and example plots. Teams refer to the register before publishing any striking image or curve. This simple habit shrinks the space for avoidable controversy and keeps attention on measurements that survive conservative treatment. The overall arc is incremental and test-driven. Each measurement either narrows the range of natural mechanisms or, in the rare case that an extraordinary signature appears, elevates the need for a different class of explanation. Most outcomes will be quiet, neutral colours during a brief spike, centroid agreement within errors, tail angles returning to nominal, and an ephemeris that prefers a tiny time-localised push only in the minutes after the Mars pass. Those quiet outcomes are the point. They turn a viral moment into bounded physics. In summary, the next phase is straightforward. Repeat the most discriminating measurements at predicted phases, keep reduction standardized and transparent, and let consistent multi-instrument evidence decide whether the Mars time flare was a compact jet, a small shedding event, a geometric flash overprinted on weak venting, or a short environmental effect that briefly redirected dust. The criteria for changing minds are already on the table. Repeated phase-locked spikes, early time spectra, simple polarimetry during kinks, and unbiased astrometry that either confines or reproduces a brief impulse. 3i Atlas will fade and leave quickly. The opportunity now is not to dramatise that exit, but to extract clean, falsifiable answers from a crowded minute of data, and to carry those methods forward to the next interstellar visitor that tests our instruments and our judgment in a tight window.